So now we'll discuss another new important concept which is called as the plugging mode in the induction motor. Plugging means just we are going to break the motor, or we can say we are going to stop the rotating of the induction motor. So by reversing the supply, if you reverse the phase supply of any two terminals, we are going to get the reverse synchronous speed. So because of that, the rotor speed and the synchronous speed are opposite of each other. So therefore it is going to become zero speed. So therefore, let me assume if I give A at an angle of 0 degree here, B at an angle of minus 120 degree here, C at an angle of minus 240 degree. So A, B, C. So this is the phase sequence. So it is going to rotate in this clockwise direction. A, B, C is the phase sequence. So the synchronous speed is going to rotate in the clockwise direction because this is going to first come earlier than this one and this one. So phase sequence is A, B, C. So this is the rotation of the synchronous speed or the rotating field RMF. But if you do the phase reversal of any two windings, let me do the phase reversal of these two windings. Now this is C at an angle of minus 240 and B at an angle of minus 120. So this is going to come earlier than this one and than this one. So phase sequence is in this manner now ACB. So therefore we can say that we are going to reverse this one. So rotating magnetic field is going to rotate in this direction. So we can say in the earlier case in the clockwise, now it is in the case of anti-clockwise. So we can say simply that here we are going to reverse the supply of any two terminals. We are going to reverse the rotation of the magnetic field in this air gap. So therefore slip is always equal to ns minus nr by ns. And now we will see somewhat in detail of this one. Suppose let me assume the rotor is rotating in the clockwise and the synchronous speed is also in the clockwise, and I reverse the supply. So therefore now synchronous speed in this direction and the rotor is in this direction. You can see clearly. So therefore the speed is going to get decrease, and if you still keep the same supply, it is going to start rotating in the reverse direction, in this direction, in the anti-clockwise. But before it is coming zero, just you have to off the supply. So therefore it is going to become zero speed. Within less amount of time, it is going to reach the zero speed. This is called as the plugging mode. In a plugging mode, we are going to reverse the supply voltage of any two terminals. I will analyze something more about this one. So now we are going to analyze three important regions. So you can see clearly we are going to analyze the three important regions in the torque slip characteristics, or we can say torque speed characteristics. So this is the torque and this is the speed. As I already told you, here speed is equal to 0, here speed is equal to synchronous speed. Let me assume here rotor speed is equal to 2 times of synchronous speed, and here rotor speed is equal to ns. Let me assume in this manner. So the rotor speed is equal to 0, the rotor speed is equal to synchronous speed, and the rotor speed is equal to 2 times of synchronous speed, and here the rotor speed is equal to ns. Right? It is actually negative, but I will take only the positive value because I know the graphical method. So I will take here positive only. So now I have already told you, whenever n is equal to 0 to n is equal to ns, I have already told one important point. So whenever n is equal to 0, the nr is equal to 0, so slip is equal to 1. And whenever nr is equal to ns, so slip is equal to 0. nr is equal to 0 means simply we can say standstill condition of the starting condition. Whenever the nr is equal to ns, it is said to be no load condition. Said to be no load condition. Then I have already told you, here slip is increasing in this manner. So whenever the slip is increasing from s is equal to 0 to s is equal to sm, it is said to be stable region or low slip region. Whereas from s is equal to s is equal to sm to s is equal to 1, high slip region. So therefore it is said to be a unstable region or high slip region. So this is said to be motoring mode. So whenever the slip is 0 to slip s is equal to 1, it is said to be a motoring mode. It is the induction motor. Induction machine is acting like a motor. So let me assume the synchronous speed in this direction. So rotor speed is also in the same direction as the synchronous speed, but its value is lesser than the synchronous speed. So nr is always less than ns, and both these directions are same. So here the slip formula, because the relative speed between the synchronous speed and rotor speed is ns minus nr, because both are rotating in the same direction. So slip is equal to ns minus nr by ns. Now we will go for the braking mode or the plugging mode. Braking mode is also called as the plugging mode. Then what is going to happen? Braking mode or plugging mode is we are going to reverse the supply of any two terminals. then we are going to get the reverse polarity of the synchronous speed. So we are going to get the reverse direction of the synchronous speed. But the rotor is also, it is rotating in the previous direction, which is in this clockwise, but now synchronous speed is rotating in the anti-clockwise. So what is the relative speed between them, which is ns plus nr? So therefore, synchronous slip is equal to ns plus nr by ns, because always slip is the relative speed between the rotor and the synchronous speed by ns. So s is equal to ns plus nr by ns. So now, if you substitute n is equal to ns, so here if you substitute n is equal to ns, we are going to get 2, slip is equal to 2, so s is equal to 2. Because I know the graphical method, that is the reason I am using this symbol. So therefore, here n is equal to ns, so if you substitute here, we are going to get s is equal to 2. So from s is equal to 1 to s is equal to 2, it is said to be a braking mode or the plugging mode. So it is said to be braking mode or plugging mode, because always nr should be always equal to ns. It will never be greater than ns. That is the reason. So in the braking mode or plugging mode, s is equal to 1 to s is equal to 2 only is possible in the braking mode. So I hope you have understood this concept. So because even if it's rotating in the, suppose even if it rotates, so definitely it will never be greater than this one. So we can say that slip will be always equal to 2 in this case. So I hope you have understood this concept. So now we will go for the generating mode. So generating mode we are going to discuss in a very detailed manner. Generating mode is, suppose this is the synchronous speed direction, but we are going to rotate the rotor with a speed externally we are rotating the rotor with a speed which is greater than the synchronous speed. Externally we are rotating the shaft rotor in the same direction of the synchronous speed, but its speed is very higher when compared to ns. It is said to be induction generator. So here nr is equal to ns, and let me take here nr is equal to 2 times of ns. So what is the relative speed? Relative speed is same, which is again ns minus nr by ns, because both are in the same direction. But here is nr is greater than ns, so therefore slip will be negative. So s is equal to 0 to s is equal to minus 1, because nr is equal to ns. If you substitute here, ns minus 2ns by ns is nothing but minus 1. So you are going to get minus 1. So listen carefully. S is equal to 0 to s is equal to 1, it is said to be motoring mode. S is equal to 1 to s is equal to 2 is said to be braking mode. S is equal to 0 to s is equal to minus 1, it is said to be generating mode. So in the motoring mode and generating mode, the synchronous speed and the rotor speed are in the same direction. So slip is equal to ns minus nr by ns. Whereas in the braking mode, ns and nr in the opposite direction. So slip is equal to ns plus nr by ns. So these are the important points that you always have to remember. So in the motoring mode and generating mode, ns and nr are always in the same direction. So slip is equal to ns minus nr by ns. Whereas in the braking mode or plugging mode, ns and nr in the opposite direction. So slip is equal to ns plus nr by ns. So s is equal to 0 to s is equal to 1 is said to be motoring mode. S is equal to 1 to s is equal to 2 is said to be braking mode or plugging mode. S is equal to 0 to s is equal to minus 1, it is said to be generating mode. So these are the important points that you always have to remember for your lifetime whenever you are living in this electrical engineering. So now, especially in the plugging mode, we are going to see what is going to happen. So in the plugging mode, I have already told you ns and nr in the opposite direction. So slip is equal to ns plus nr by ns. So let me add plus ns and minus ns in the numerator. So ns plus n plus ns minus ns by ns. So if we add plus ns and minus ns, we are going to get like this. So ns plus ns is 2ns. Here minus of ns minus n by ns. So if you take this one into fractions, so 2 minus ns minus nr by ns is nothing but forward slip, or can say motoring slip. So 2 minus s motoring slip. So slip of plugging is called as a 2 minus motoring slip. So this is the very important point. So therefore here I have add plus ns minus ns. So ns plus ns is 2ns. If here I will take minus, so ns minus nr by ns. If you take ns into two fractions, we are going to get 2 minus, it is called as the motoring slip. So plugging slip, or we can say plugging slip is equal to 2 minus the motoring slip. So if you want to get the plugging slip for a particular speed of rotor, it is the plugging slip is equal to 2 times the motoring slip. So plugging slip is equal to 2 minus motoring speed. So always plugging slip is equal to 2 minus of motoring speed for a particular value of the rotor speed, or a particular value of the rotor speed. So plugging slip is equal to 2 minus of the motoring slip. Now we will analyze one important thing that you always have to remember, this is the overall diagram. This is the overall diagram of each and everything of the induction motor. So this is the torque and this is the speed. So therefore I have already told you here speed is equal to 0, speed is equal to ns, and here speed is equal to 2 times of ns, and here speed is equal to ns. I have already told all these things. It's a rotor speed. Actually we are taking the rotor speed. Rotor speed is equal to 0, nr is equal to 0, nr is equal to ns, nr is equal to 2 times of ns, nr is equal to ns here. So let me discuss the motoring mode. I have already told you in the motoring mode, whenever nr is equal to 0, slip is equal to 1. Whenever nr is equal to ns, slip is equal to 0. S is equal to 1 is said to be, we can say that nr is equal to 0 means standstill or starting condition. So whereas nr is equal to ns will be said to be no load condition. So s is equal to 0 to s is equal to 1. So we are moving in this direction. So s is equal to 0 to s is equal to Sm. It is said to be a low slip region or stable region. So therefore torque is directly proportional to s. As the s increases, the torque increases. Whereas from Sm to s is equal to 1, it is said to be high slip region or unstable region. So therefore as the slip increases, the torque will decrease. You can see clearly in this diagram. So this is said to be a motoring mode because ns and nr are in the same direction of rotation, but ns is always greater than nr. So ns and nr are rotating in the same direction, but ns is always greater than the nr, and the slip is equal to the relative speed between the ns and nr by ns, which is ns minus nr by ns. Now we will go for the plug-in mode or the braking mode. See, plug-in mode or braking mode is very simple. Here we are going to interchange the supply of any two terminals of the stator. So we are going to get the reverse rotating magnetic field. So therefore nr is in this direction and ns in this direction, only because we are going to stop this motor in a very small amount of time. We want to bring the rotor speed to 0 in a very small amount of time. So we are going to use this plug-in method. So you can see clearly ns and nr are both are of opposite of each other. Then the relative speed is nothing but ns plus nr. So slip is equal to the relative speed by ns, which is s is equal to ns plus nr by ns. So whenever nr is equal to ns, if you substitute here, we are going to get s is equal to 2. So s is equal to 2. So s is equal to 1 to s is equal to 2 is said to be braking or plug-in mode. So ns and nr are quite opposite of each other of rotation. So now we will discuss. So now we can see clearly the torque is going to get decreased in this manner. In this manner, you are going to get the torque decrease in this manner. You are going to get like this, and finally you are going to get the zero torque here. So you can see clearly you are going to get zero torque in this way. So this is the graph that you are going to get. So now we will see what is going to happen for generating mode. For generating mode means externally we are rotating the rotor speed, which is greater than the synchronous speed, and it is rotating in the same direction of the ns. So nr is very high than ns. By externally we are rotating this one. By externally, with the help of turbine, we are rotating the shaft of the induction motor with a very high speed. Now it is going to act like induction generator. So both are in the same direction. So relative speed is ns minus nr. So what is the overall slip? Slip is equal to ns minus nr by ns. So as nr is greater than ns, slip is a negative. So therefore this is s is equal to 0. If you substitute nr is equal to 2 into ns, you are going to get here s is equal to minus 1. So minus 1. So s is equal to 0 to s is equal to minus 1 is said to be generating mode. So torque you are going to get negative manner. So this is the torque that you are going to get. So finally this is the torque we are going to get. So this is the diagram of the torque we are going to get. I have already told you in the low slip region, torque is directly proportional to s. As s is equal to 0, torque is also 0. So this is the point that you always have to remember. So this is the overall torque diagram that you are going to get for the plug-in mode or braking mode or motoring mode or the generating mode. So this is the overall torque diagram which you always have to remember. It is going to give you each and everything in a very much detailed manner, and I want you to remember this one for all your lifetime whenever you are living in this electrical engineering. So s is equal to 0 to s is equal to 1 is said to be a motoring mode, and s is equal to 1 to s is equal to 2 is said to be a plug-in or braking mode, and s is equal to 0 to s is equal to minus 1 is said to be a generating mode. So all these things that you always have to remember for your lifetime till you live in this electrical engineering subject. So now we are going to see some different views which are very much useful. We are going to see each and everything. Suppose there is a three-phase line, and here this is an induction motor. We are going to connect to these three-phase lines. Then I am going to connect a load to this shaft. See, as we are going to connect this induction motor to this three-phase supply line, this induction motor is going to take the active power and the reactive power from this supply. So listen, induction motor is going to absorb the active power and reactive power from this mains three-phase supply lines. So it is going to draw the active power and reactive power from the supply lines. Active power because for producing the torque on this load, and the reactive power for producing the RMF or the flux rotating magnetic field. So listen carefully. It is absorbing the active power and reactive power from the three-phase lines, and the active power is used to produce the torque on the load, and the reactive power is taken from the three-phase line to produce the flux means rotating magnetic field. So therefore, I have already told you power is equal to torque into omega. So torque is equal to P by omega. So which is P by 2 pi n by 60 means 60 by 2 pi n into P. So active power is drawn to produce the torque on the load. So therefore, whenever you connect a induction motor to a three-phase lines, the induction motor is going to accept the active power which is useful for producing the torque on the load, and it is going to draw the reactive power to produce the reactive power for producing the flux in the rotor. So therefore, this is NS and this is NR, both are in the same direction. So you can say clearly that it is going to draw the reactive power for producing the torque on the load and reactive power for producing the rotating magnetic field, and NS and NR are in the same direction because it is acting like induction motor, and NR is always less than NS. Suppose now I am going to do something very different. Suppose if I connect a prime mover, instead of load, I will remove the load and I will connect the prime mover. With a speed which is, I am going to rotate the shaft at a speed of NR, and I will see what is going to happen. So therefore, you can see clearly here, we see this induction motor is going to draw the reactive power from the three-phase lines to produce the responsible flux. And here NR is always greater than the NS. So therefore, we can say it is producing the active power to these three-phase lines. So listen carefully. I am rotating the NR with a speed which is greater than the synchronous speed. So therefore, it is going to produce the active power to these three-phase lines. So induction motor is going to act like induction generator, and it is giving the active power to the three-phase lines, but it is drawing the reactive power from the three-phase lines to produce the RMF in this machine. So we can say clearly, so therefore now it is giving the active power to the three-phase lines and accepting the reactive from the three-phase lines to produce the RMF in the machine. So it is basically acting like an induction generator. If NR is greater than NS, then it is acting like induction generator, and always it is working at the leading power factor. So it is going to act like a leading power factor. So this is called as the leading power factor. So this is called as the always leading power factor. So this is called as always a leading power factor. So this is how to remember. Whenever NR is greater than NS, it is acting like an induction generator, and it is always acting in a leading power factor mode. So now I will see another important view. Suppose this is a synchronous generator. So this is the field winding we are going to give, or we can say excitation. So here we are going to rotate this rotor, because shaft winding in the stator we are going to keep the coils to produce the current. So therefore, whenever you with the help of prime mover you are trying to rotate this rotor and you are going to give the field excitation, then this synchronous generator is going to deliver the active power and also reactive power to the nodes. So therefore, we can say that here this prime mover is rotating this rotor and field excitation we are giving. So therefore, this synchronous generator is delivering the active power and also reactive power to the nodes. So this is basically synchronous generator. So mechanical input gives power to load. So as you are going to give the prime mover, because of this we are delivering the active power to the load. So excitation input gives the Q to load. So because of excitation, we are going to produce the reactive power which is delivered to the load. So because of prime mover, we are delivering the active power to the load, and because of excitation, we are going to deliver the reactive power to the load. So these are the points that you always have to remember. So with the help of mechanical input, we are going to deliver the active power to the load, and with the help of excitation input, we are going to deliver the Q to the load. So we can say that with the help of mechanical input, we are delivering the active power to the load, and with the help of excitation, we are delivering the reactive power to the load. So overexcited means we are supplying the Q at lagging power factor, and underexcited means we are drawing the Q at a leading power factor. See, so listen carefully. Overexcited means supplying Q. So overexcited means supplying Q. So therefore overexcited means we are supplying the Q. In that mode, the generator is going to act like a lagging power factor mode. See, I have already told one important point. In the overexcited region, the synchronous generator will be acting like a lagging mode. So I have already told this one. In the quite opposite manner, in the unexcited region, it is drawing the Q. It is acting like a leading power factor. All these things I have already told you. So in the overexcited region, in the overexcited, this synchronous generator is going to deliver the Q, supplying Q to the load. So it is going to act like a lagging power factor. Whereas in the underexcited mode, it is drawing the Q and it is acting at a leading power factor. All these things I have already told. Because in the overexcited region, the single generator means G means lagging, motor means leading. Here it is quite opposite. So I have already told all these things. So in the overexcited region, the single generator is supplying the Q at lagging power factor, and in the underexcited region, it is drawing the Q at leading power factor. So with the help of prime mover, it is delivering the active power to the load, and with the help of excitation, it is delivering the reactive power to the load. So this is the one important concept. Let me assume this is an induction generator, and here I am going to use the prime mover. See, with the prime mover, I am rotating the rotor speed at a speed which is very high. See, and we are going to connect a load to this one. See, as there is no rotating flux, even though how much you rotate, there is no rotating flux. So therefore, we can say that the active power is 0 and the reactive power is 0, because there is not even any rotating magnetic field, because there is no current in the stator. So therefore, we can say that here with the active power delivered to the load and the reactive power delivered to the load is 0, because there is no supply to that. There is no reactive power which is present in the induction generator to produce the RMF. So we can say the active power delivered and the reactive power delivered to the load is 0. Suppose now for this induction generator, I will provide a capacitive bank. If I provide the capacitive bank, what is going to happen? So this induction stator is going to draw this capacitive reactive power, and it is going to produce the RMF, rotating magnetic field, and if NR is greater than NS, it is going to deliver the active power to the load. So this is a very important point. This induction generator is accepting this reactive power to the stator coils, it is producing the RMF, and whenever NR is greater than NS, it is going to produce the active power which can be given to the load. So these are the important views that you always have to remember for your lifetime. See, now we will see something very much important. It is called as the equivalent circuit diagram of a three-phase induction motor. So equivalent circuit diagram of a three-phase induction motor. So equivalent circuit diagram of three-phase induction motor with a D-bar rotor. That's a very important point. Equivalent circuit diagram of a three-phase induction motor with a D-bar rotor. I have already told these important points. This is the stator resistance, stator leakage reactance. This is the core loss, we can say core loss resistance, which is called as the magnetizing reactance. This is called as the, you can say, leakage reactance of the rotor, and this is called as the rotor resistance. So in the easy representation, I have already told you, because SE2 means here R2 and JX2. So divide by S, we are going to get R2 by S and X2 and E. So this is X2, this is R2 by S. So like that. So therefore now you can see clearly, now I am going to compare all these parameters, how we are going to get. So now RS is always less than this value. So RS is always less than this value, and this 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 is always less than this value. I have already told you RC is very high, because here IC is very less, because IM is very huge value. So therefore RC, see, RC is a very huge value, then comes the XM, So RC is always greater than XM. So this is the very highest value, and the second highest value is this one. So these are the two things that you always have to remember. And least value is the stator resistance. So this is the very highest, second highest, and the least highest is this value. So RS is less than this value is less than this value, this value is less than this value, this value is less than this value, this value is less than this value. So we can say first highest, second highest, and least highest. So these are the three things that you always have to remember. We can say the reactance, or you can say the rotor. We can say this is called as the core loss resistance is always higher when compared to magnetizing reactance, and the least one was the rotor resistance. So RS is less than R. This is called the rotor. This is R dash, and this is less than this one. This less than this one. This less than this one, and this less than this one. So this less than this one. This less than this one. This less than this one. This less than this one, and this less than this one. So always remember, RS is first highest, second highest is XM, and the least highest is RS. If you know these three things, you can easily go for the option checking. So this is less than this one, this is less than this one, this is less than this one, and this is less than this one, this is less than this one. So this is less than this one, 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 and this is less than this one. So first highest is RC, second highest is XM, least highest is RS. If you know these things, it is very much useful. Now we will discuss one important concept in the induction machine, which is the different rotor types and its diagrams. So there are different types of rotors that we are going to use in the induction machine. All those things now we are going to discuss in a very detailed manner. So different types of rotors. So different rotor types and its diagrams. Each one we are going to learn one after the another in a very easier manner. So you can see clearly here, this is called as the deep rotor bar. See, D bar rotor means this is the rotor. So you can see there is a huge amount of deep. You can see the depth is very high. So you can see depth is also not in a uniform format. Here the depth is very less, the width is very less, but as you go inside, the width is very high. So therefore you can say it is said to be a D bar rotor. It's a D bar rotor because initially the width seems to be very less, but as you move inward, you can see the depth is somewhat higher, so it is called as a D bar rotor. Whereas this is called as this type of rotor. If the width is same, if you go inside the slot, it is said to be slip ring rotor because the width is uniform. It is called as a slip ring rotor. Otherwise, if the width is not uniform, if you go inside, it is said to be a D bar rotor. Otherwise, if the width is uniform, if you go inside it, it is said to be a slip ring rotor. Let me discuss the other one. See, this is the rotor. If the rotor is in this shape, so you can see initially the uniform is very less, the width is very less, but you go inside, the width is uniform here also, but here also the width is uniform, here also width is uniform, here width and here width are different. This width is somewhat higher when compared to this width. It is said to be normal squirrel cage rotor, So this is said to be D bar rotor, this is said to be slip ring rotor, and this is said to be normal squirrel cage rotor. And the last one is called as the double cage rotor. So this is the rotor, you can see clearly. Here we are going to use two type of slots. This is called as the outer cage. It is basically manganese and brass. It is made by manganese and brass, whereas the inner cage is made by the copper. The inner cage is made by the copper and the outer cage is made by the manganese and the brass, and the inner cage is made by the copper. You can see clearly it is in the format of a rectangular shape, or where the upper part is made in terms of the circular shape. So this is the thing that you always have to keep in your mind till you die in this electrical engineering. So the upper part is somewhat circular and the inner part is somewhat rectangular in shape, and this is said to be outer cage, and this is called as the inner cage, and the outer cage is made by the manganese and the brass, and the inner cage is made by the copper. So this is called as the double cage rotor. So these are the four different types of rotor types which are mostly used in the induction machine. So you can see clearly as you go inside here, the width is very less, but as you move forward, the width goes on increases. So it is said to be a D bar rotor. Whereas here the width is uniform. If you go inside, it is said to be a slip ring rotor. Whereas here the width here is uniform. Here also width is uniform, but there is a sudden increase of width. This is called as a normal squirrel cage rotor, and here there will be two types of slots. One is the circular slot and one there is called the rectangular slot, and this is called as the outer cage and this is called as the inner cage. Outer cage is basically made by the manganese and the brass, whereas the inner cage is made by the copper. So this is the double cage rotor because there are two types of rotor slots of different nature. One is circular and one is a rectangular. One is made by the manganese and brass and the other is called as the copper. This is called as the outer cage and this is called as the inner cage. So D-bar rotor, slip ring rotor, normal squirrel cage rotor and a double cage rotor. So these are the four different types of rotors that are mostly used in the induction machine. So now we will discuss each and everything, the torque versus speed characteristics of these four different types of these armature rotors. See, first one is called as the first thing what we have discussed is called as the D-bar rotor. So D-bar rotor means shortcut DBR. So for DBR, this is the nature of the torque speed characteristics. So torque speed characteristics you are going to get like this. This is the rotor speed is equal to 0 and the rotor speed is equal to synchronous speed. So this is the nature you are going to get the torque with respect to say speed for a double or you can say D-bar rotor. DBR means D-bar rotor. And the next one we have discussed is about the slip ring rotor. Slip ring rotor means its notation is SRR. So SRR. So this is called as a slip ring rotor. So this is the characteristics of the slip ring rotor. So torque speed characteristics. If you see clearly, the slip ring rotor has a higher torque when compared to D-bar rotor. So initial. So we can say the initial torque or the starting torque of the slip ring rotor is very high when compared to D-bar rotor. And the third one is the normal squirrel cage rotor. Normal squirrel cage rotor means NSCR. So this is the normal squirrel cage rotor characteristic with respect to torque and speed characteristics. So you can see clearly, as you can see clearly something, the starting torque of the normal squirrel cage rotor is very less when compared to the remaining two. So the starting torque of normal squirrel cage rotor is lesser than the double D-bar rotor is lesser than the slip ring rotor. So these are the characteristics torque with respect to say speed for these three different types of the rotors: D-bar rotor, slip ring rotor and the normal squirrel cage rotor. And now we will go for the another type of rotor which is called as the double cage rotor. Double cage rotor has two things. One is called as the outer cage rotor and the other one is the inner cage rotor. It is a combination of these two things. So this is for the outer cage rotor and this is for the inner cage rotor. So this is the torque speed characteristics of the outer cage rotor and this is the torque speed characteristics of the inner cage rotor. So if you do the addition of these two graphs, you are going to get the resultant which is called as the double cage rotor. So this is the torque speed characteristics of the double cage rotor. So you can see clearly the starting torque because of the inner cage rotor is very high when compared to starting torque of the outer cage rotor. So the starting torque of the outer cage rotor is very high when compared to starting torque of the inner cage rotor. It's a very important point. The starting torque of the outer cage rotor is very higher when compared to the starting torque of the inner cage rotor. If you do the addition of these two graphs, we are going to get the resultant graph which is called as the double cage rotor. So this is called as the D-bar rotor and this is the slip ring rotor and this is the normal squirrel cage rotor. And this is called as the outer cage rotor, this is the inner cage rotor and this is the double cage rotor. So these are the graphs that you always have to remember. This is called as the D-bar rotor, this is called as the slip ring rotor and this is called as the normal squirrel cage rotor and this is called as the outer cage rotor and this is the inner cage rotor. Outer cage rotor starting torque is higher than the inner cage rotor and if you do the addition of these two graphs, we are going to get the resultant graph which is called as the double cage rotor. So now we will discuss the equivalent circuit diagram of the double cage induction motor. So double cage induction motor means the last one we have studied. So here this is the torque speed characteristics of the double cage rotor. So for this the equivalent circuit diagram we are going to represent with respect to stator. So equivalent circuit diagram of double cage induction motor means outer cage and inner cage. Outer cage is made by manganese and brass and the inner cage is made by copper. All these things I have already told you. So now if you draw the equivalent circuit diagram with respect to stator, you are going to get in this format. So you can see clearly this is the R1, this is X1, this is the RC, this is XM, this is RI dash by S, this is xi dash, this is r naught dash by s, this is x naught dash. So this is with respect to inner cage and this is with respect to outer cage. See, all this diagram is with respect to stator. R1 is called as the resistance of the stator, or we can say the resistance of the stator, and X1 is the leakage reactance of the stator. RC is called as the coreless component of resistor, and Xm is called the magnetizing reactance. This is Ri dash by S, Xi dash. It is representing the inner cage. R naught dash by S, X naught dash by X naught dash is called as the outer cage. All this diagram is with respect to stator. So it is the equivalent circuit diagram of double cage induction motor. So it is the equivalent circuit diagram of double cage induction motor. So this is the equivalent circuit diagram of the double cage induction motor. So now we will discuss one important concept which is called as the crawling. So crawling means running slowly. See, crawling means running slowly. Crawling basically means running very slowly. Crawling means running very slowly. Why we have to run very slowly? Because why induction motor runs very slowly? Because now we will see what is the exact behavior of the induction motor. What is the nature for running it very slower. So crawling means we can say basically running very slowly. Means running very slowly. So you can say clearly this is a stator and this is a rotor. So the flux between the stator and the rotor, if it is a pure sinusoidal, so this is the flux diagram between the stator and the rotor. See, pure sinusoidal flux distribution, whatever the flux between the stator and the rotor, if it is a pure sinusoidal, so it's a pure sinusoidal flux distribution. This is ideal case. Ideal case, whatever the flux between the stator and the rotor will be in a pure sinusoidal flux distribution, but practically this is not the case because the stator has some type of slots and the rotor will also have the slots. So because of that, there is a distortion. There is a distortion in the flux which is between the stator and the rotor, and it will never be a pure sinusoidal waveform, or we can simply say non-sinusoidal flux distribution. So because of this nature only, the induction motor is trying to rotate very slowly when compared to its nearly equal to ns. See, always induction motor speed should be nearly equal to ns, but due to these reasons it will run very slowly. You can say due to the slots in the stator and the slots in the rotor, the flux distribution between the stator and the rotor will never be a pure sinusoidal waveform. So there will be distortion in the flux. So therefore, because of this, it will run very slower. So therefore, we can say that because now you can see clearly whatever the flux distribution between the stator and rotor is not a pure sinusoidal, or you can say non-sinusoidal flux distribution. So because of this, we can say its behavior is like this. So it is going to have a crawling nature. So the crawling is going to happen in induction motor because of the non-sinusoidal flux distribution. So now you will see whenever there is a non-sinusoidal means Fourier series is going to get applied. So you are going to get lot amount of harmonics frequencies. So now we will discuss the different types of harmonics. Harmonics in non-sinusoidal flux distribution, because non-sinusoidal flux distribution means definitely we can analyze this with the help of Fourier series. So it is going to be a huge amount of harmonics. So each and everything harmonics we are going to discuss in this non-sinusoidal flux distribution. So harmonics in the non-sinusoidal flux distribution we are going to see. See, harmonics are categorized into two parts. One is called as the even and odd. See, we are going to learn only the odd harmonics but not the even harmonics in our course. See, in our course, harmonics are of two types. One is even harmonics and odd harmonics. But we are going to discuss only the odd harmonics but not the even harmonics. See, odd harmonics are categorized into three types. One is 3m, 3m minus 1, 3m plus 1. You can go for either m or either n notation. Everything is same. So 3m, 3m minus m, 1 and 3m plus 1. See here, m should be even, here also m should be even, but here m should be odd. Then only you are going to get the odd frequencies. So if you substitute m is equal to 1, you are going to get 3. If you substitute m is equal to 3, you are going to get 9. If you substitute m is equal to 5, you are going to get 15, like that. If you substitute m is equal to even, so you cannot substitute 0, substitute 1, so substitute 2, so you are going to get 5, so like that. So basically we can say that, see, this is the very easy way to see this one. So harmonics are two types. One is even and odd. We are going to discuss only the odd harmonics, which is the odd harmonics are categorized into three parts: 3m, 3m minus 1 and 3m plus 1. Here we are going to use m as even number. Here we are going to use m as odd number. So we are going to get like this: 3, 9, 5. All these are odd numbers. Whereas 5, 11 are also odd numbers. 7, 13 are also odd numbers. So this is a positive, this is a negative. Then plus 0. So this is the easy way to remember: plus 1, minus 1 and plus 0. So these are all 0 sequence components. These are negative sequence components. These are always positive sequence components. This is the easy way to remember. So plus means all these are positive sequence components. Minus means negative sequence components. Plus 0 means these are the 0 sequence components. So this is the easy way to remember. So all harmonics means 3m, 3m minus 1 and 3m plus 1. Here m is equal to even, here m is equal to odd. So this is the point that you always have to remember. So now we will discuss something more about further analysis of these harmonics. Fundamental. So fundamental, let me take the fundamental, the original harmonics. Phi a is equal to, let me take the fundamental fluxes. Phi a is equal to phi m sin omega t. Phi b is equal to phi m sin omega t minus 120. Phi c is equal to phi m sin omega t minus 240. So you can see the phase difference between the fluxes is 100 degrees between them. So now third harmonics. See, I want to know what is the third harmonic components of the fluxes. Phi a3 is equal to phi m3 into sine of 3 omega t. Phi m3 into sine of, just multiply by 3. So 3 into omega t minus 120. And phi c3 is equal to phi m into sine of 3 into omega t minus 240. So if you do the analysis of this one, again you are going to get here, which is phi m3 sine 3 omega t. Here phi m3 sine 3 omega t. Phi m3 sine 3 omega t. So therefore you can see all these are in the same phase with respect to axis. So we can say these are said to be 0 sequence components. So now, so third harmonics, or we can say 3m harmonics, always 3m harmonics are said to be, 3m harmonics are said to be always in the same phase. Now go for the fifth harmonics. So fifth harmonic means I can say it is belongs to 3m minus 1. So therefore fifth harmonic means phi a phi is equal to phi m phi into sine phi omega t. Phi b phi is equal to phi m phi into sine of phi into omega t minus 120. It is nothing but phi m phi into sine of phi omega t minus 240. So therefore here simply phi c phi is equal to phi m phi into sine of phi into omega t minus 240. If you simplify this one, we are going to get phi m phi into sine of phi omega t minus 120. So now you can see the phase difference is reversed. It is opposite to the original phase. Initial phase in the clockwise was ABC, but now in the anti-clockwise it is ABC. So therefore we can say the phase was opposite. So it is opposite sequence. So it is called as the negative sequence components. Now go for the seventh harmonic. Seventh harmonic is belongs to 3m plus 1 category. So phi f7 is equal to phi m7 into sine of 7 omega t, and phi b7 is equal to phi m7 into sine of 7 into omega t minus 120, which is phi m7 into sine of 7 omega t minus 120. If you do simplification, you are going to get same thing like this. So therefore phi c7 is equal to phi m7 into sine of 7 into omega t minus 240. If you do the further analysis, you are going to get the same thing like this: phi m7 into sine of 7 omega t minus 240. So now original fundamental phase sequence in the clockwise was ABC. Here also now in the clockwise same, which is ABC. So we can say same sequence as the original one. So it is said to be a positive sequence component. So this is the point that you always have to remember. So 3m harmonics are always 0 sequence components. 3m minus 1 components are always odd, or you can say negative, or you can say negative sequence components. And the seventh, or you can say 3m plus 1 components are always positive sequence components. So this is the thing that you always have to remember till you die in these electrical engineering concepts. So therefore 3m harmonics are always 0 sequence components, and 3m minus 1 components are always odd, or you can say negative sequence components, and 3m plus 1 are always positive sequence components. So this is the thing that you always have to remember. So ms is called as the fundamental speed. So fundamental speed means it is the speed at which the flux is rotating. It is the speed at which the flux is rotating. So ns is equal to fundamental speed. It is the speed at which the flux is rotating. If you go for the fundamental A, B, C in the clockwise direction, so we can say that it is rotating in the clockwise. Let me assume it is rotating in the clockwise in this format. Suppose here ABC is in the clockwise, so therefore the actual speed of the fundamental frequency, or the fundamental we can say ns is in the clockwise direction. Let us assume ns is equal to fundamental speed. Now fifth harmonic speed is how much? So fifth harmonic speed is nothing but 120 f by p. So therefore now, so what is the fifth harmonic speed? So fifth harmonic speed is very simple. Just go for the ns by phi. Just go for the ns by phi. So ns is equal to 120 f by p. just give a division by 5. And seventh harmonic speed is very simple, ns by 7, which is 120f by p by 7. So therefore, ns is called the fundamental speed, and fifth harmonic speed is ns by 5, and seventh harmonic speed is ns by 7. So now I want to find what is the slip at the seventh harmonic. So slip because of seventh harmonic. I've already told you here. See, ns is because of fundamental frequency. So ns by 7 is because seventh harmonic. Seventh harmonic belongs to which category? I've already told you. It is a same phase sequence, positive phase sequence. So ns and ns by 7 are in the same direction. So therefore, the relative phase difference is ns minus ns by 7 by ns. So you are going to get 6 by 7, which is less than 1. Whereas fifth slip, if you want to find with respect to fifth slip, see, ns is because of fundamental fluxes, fundamental components, whereas ns by 5 is because fifth harmonic is nothing but it belongs to negative sequence component. It is opposite to the phase sequence of the original one, so it is rotating in the reverse direction. So therefore, what is the overall phase difference? ns is in clockwise and fifth harmonic speed is in the anti-clockwise, so both are going in the opposite direction. So the relative phase difference between them is in the positive. So therefore, the relative speed is not due by the addition. So ns plus ns by 5 by ns. So you are going to get 6 by 5, which is greater than 1. So this is the only thing that you always have to remember. Due to fundamental fluxes, you are going to get the synchronous speed ns. Let us assume the clockwise sequence of the fundamental flux is A, B and C. So therefore, the ns is also rotating in the fundamental direction. Whereas the 3m components are always zero sequence components. Whereas the 3m minus 1 are the negative sequence components, they are rotating in the reverse direction. They are always opposite to the fundamental frequencies. So therefore, they are going to move in the anti-clockwise direction, which is opposite to the original phase. Whereas the 3m plus 1 are the positive sequence components, they are going to move in the same direction as the original phase. So in the same direction as ns, clockwise. So with the help of these things, that you need to always analyze the speed of the fifth harmonic component is ns by 5, and the speed of the seventh harmonic component is ns by 7. Similarly, if you want any other speed, which is the speed of the 11th harmonic component is ns by 11. Similarly, the speed of the 13th harmonic component is ns by 13. So like this, you have to always remember ns is equal to 120f by p. So this is the thing that you always have to remember. Then you can easily go for the analysis. You are going to get the solutions. So only thing that I want to tell you in finally, if you assume the original fluxes A, B and C are in the clockwise direction, the phase sequences A, B, C in the clockwise direction, then 3m components are zero sequence components and 3m minus 1 components are the negative sequence components. They are going to rotate in the opposite direction, or simply their phase sequence is negative, so therefore they are going to rotate in the opposite to the original phase. Whereas 3m plus 1 are the positive phase sequence components, they are going to rotate in the same direction as the original phase. ns is because of original phase, let me assume the clockwise, then definitely 3m minus 1 components are going to rotate in the opposite, which is in the anti-clockwise. Similarly, 3m plus 1 means they are going to rotate in the same direction as the original phase, which is in the clockwise direction. So now we can say that the speed of fifth harmonic component is ns by 5 and the speed of seventh harmonic component is ns by 7. So this is the point that you always have to remember. So now what is the net flux? Net flux is because of each and every harmonic. So you have to add the net flux is because of each and every harmonic. So each and every harmonic. So phi 1 is the fundamental component. So we have taken this, phi 1 is called the fundamental component. So fundamental component, I have already told you, the fundamental component frequency, I have already told you, phi 1 is nothing but the fundamental components, the ABC are in the clockwise direction, and you have to go for all the harmonics. So phi 5, phi 7, all the harmonics you have to add, then you are going to get the net resultant flux. It is not at all a pure sinusoidal waveform. So here, whatever the original phase I have taken, this is for the fundamental component. Phi 1 is nothing but fundamental component, which is the original flux, which is ABC in the clockwise direction. I have assumed where ns is the speed because of this flux, because of this phi 1. Then phi 5, phi 7, everything we have studied. So therefore, you have to add all these fluxes to get the overall flux phi net, and it is not a pure sinusoidal, it is a distorted waveform. All these things I already told you. ns is the speed because of this fundamental component, and ns by 5 is the speed with respect to fifth harmonic component, and ns by 7 is the speed with respect to seventh harmonic component. Like that you have to do this one. And the positive sequence components are going to rotate in the same direction as the fundamental components, and the negative sequence components are going to rotate in the opposite direction of the fundamental component. So this is what I am trying to tell you from the starting onwards. So you can see clearly this is the phi 1. Phi 1 is the fundamental flux. So this is the fundamental flux. This is the phi 1, and this is the phi 3, third harmonic flux. Like that you will get the phi 5 and phi 7. Like that you are going to get for each and everything. We have to add all these things to get the overall net flux. It is a purely, or we can say, non-sinusoidal waveform. Ns is the speed because of this flux. Ns is the speed because of this fundamental component. Ns by phi is because of phi component. So now we are going to compare between the squirrel cage and the slip ring induction motor. So we are going to compare the comparison, the difference between the squirrel cage induction motor and the slip ring induction motor. So we are going to compare the squirrel cage induction motor and the slip ring induction motor. So this is called a squirrel cage and this is a slip ring. So effective air gap, effective less air gap. The air gap is very less between the stator and the rotor, whereas the effective more air gap. So more gap, see in a squirrel cage induction motor, we can say there is a less amount of air gap between the stator and the rotor, but in the slip ring induction motor, the air gap between the stator and the rotor is very higher. So as the air gap is less, the IM is very less to get the required flux. Here the air gap is more, so we need IM very high to get more flux. So here power factor is very better. So as we can say less effective air gap. So less effective air gap means less leakage reactance. So less leakage reactance means we can say power factor is nothing but R2 by ln to R2 square plus X2 square. As X2 decreases, the cos phi increases. So we can say the power factor is better, whereas here more effective air gap means more amount of flux, leakage flux. So we can say more amount of leakage flux means more amount of leakage reactance. So therefore definitely we can say as denominator cos phi 2 is equal to R2 by ln to R2 square plus X2 square. As X2 increases, the power factor will decrease. So less overhang, so high efficient. So there is no winding on the squirrel cage motors. So we can say there is no overhang because we are not winding anything. So there is no overhang. So therefore it is highly efficient. So high overhang, so less efficient because we are going to winding. We have to do some winding on the rotor. So there is some hanging part is also present. So because of that, efficiency is very less. Torque is very maximum. The torque is very maximum because of squirrel cage, whereas the torque is less maximum. The maximum value is very less when compared to squirrel cage 1. It's a robust, it's a rigid, and highly it can be loaded. So it is it's a robust, it's a rigid, and highly it can be loaded. Means you can have more amount of heavy loads, still it can rotate it. It's a very robust design, it's a very rigid, and it can load, if you load any huge quantity, still it can rotate. It is less robust, means it can't withstand huge amount of load. This squirrel cage induction rotor is very less weight, and because there is no extra winding, so we can say it is less weight, but here we are going to put the extra windings, so the weight will increase. The less resistance of rotor due to least overhead. So because we are not going to keep any external resistance wires, so therefore the rotor resistance is very less, but comparatively more due to overhead, because we are going to keep some extra resistance also we can add. So we can say this has huge resistance when compared to this one. So here we are going to get the bigger circle diagram and lesser circle diagram, and the winding with insulation requires more slot sides. See here the squirrel cage induction motor has a bigger circle diagram, but here we are going to get lesser circle diagram, and the winding with insulation requires a more slot size. So we need more amount of slot size, and also it needs more amount of insulation. So lesser circle diagram with winding, and winding with insulation requires more slot size. So we need huge amount of slot size, and also more amount of insulation. So skewing reduces the efficiency and removes the crawling and cogging. So therefore skewing. So if you do the skewing reduces the efficiency and removes the crawling and the cogging. So if you do the skewing of the slots, just you see basically in ideal case all the slots should be in the straight line, but we are going to skew it in certain direction. So with the help of this we are going to remove the crawling and clogging also, but efficiency is going to be reduced. See, by screwing means you are going to just move the slots in somewhat a parallel direction. They are not straight, they are somewhat parallel. So we can say that with the help of this we can remove the clogging and crawling. But even though we are going to remove the clogging and crawling, but still the efficiency is reduced. So this is a very important point that you always have to remember till by on this paragraph. So we can, so let me explain again in detail regarding the comparison of the squirrel cage induction rotor and the slip ring induction rotor in a very easier manner. In a squirrel cage, the air gap between the stator and the rotor is very less. So, but whereas in the slip ring induction motor, the more air gap between the stator and the rotor. As here, the air gap is less, so we need less amount of magnetizing current to produce a flux. Whereas here, as the air gap is more, we need more amount of magnetizing current to produce a given flux. Here, as the less amount of air gap, so less leakage reactance, so cos phi is equal to R2 by under root over R2 square plus X2 square, and X2 decreases, the power factor increases. So power factor is better here, but here the X2 increases, so therefore the power factor is low. Here less overhang, so high efficient, because we are not going to provide any external winding, so there is no on the rotor, so it is not having any overhang, so it is highly efficient. Whereas here we are going to keep the huge amount of overhangs, external resistance we can add with the help of winding on the rotor, so it has high amount of overhang and is less efficient. Whereas here the torque is very maximum. The torque is very maximum in case of squirrel cage when compared to slip ring. So squirrel cage induction motor has the huge amount of starting torque is maximum when compared to here. The maximum torque of squirrel cage induction motor is very high when compared to slip ring induction motor. And squirrel cage induction motor is very robust. It's very rigid. It's a very robust and very rigid, and highly it can be loaded. Here it is less loaded. Means we can add huge amount of load for squirrel cage induction when compared to slip ring. Whereas this squirrel cage is very less weight when compared to this one, because here we are not going to provide any winding on the rotor, so it is less weight. Whereas in the slip ring we are going to keep some winding, so its weight will increase. As there is no overhang, we are not going to keep any winding on the rotor, so its resistance is very less, and the starting torque is also very less. So less resistance of rotor due to least overhang, whereas here comparatively more due to overhang, because we are going to keep more amount of external winding on this rotor, so resistance increases and the starting torque is also increases. Here we are going to get the bigger circle diagram in the squirrel cage induction motor, whereas here we are going to get the less circle diagram, and the winding with insulation requires more slot sides. So here the circle diagram is very lesser, and we need more amount of slot sides with more amount of insulation. And we are going to do the screwing. We are going to do the screwing of the rotor bars in such a direction. So therefore, here screwing is going to remove the clogging and crawling, but it is going to remove the clogging and crawling, but the efficiency will decrease. Even though it is removing the clogging and crawling, but the efficiency is going to get decreased. You will get something by losing something. Always in life also, you are going to get something by losing something. If we want to remove the clogging and crawling, just screw it, but efficiency is going to get decreased. So this is the comparison between the squirrel cage and the slip ring. So now we are going to discuss the inverted induction motor. Inverted induction motor. So inverted induction motor means, now instead of giving the supply to stator, we will give supply to rotor, and we will see what is the consequences. So this is the stator and this is the rotor. Now we are going to give supply to the rotor but not the stator, and you will see what is the consequences. So I am going to give supply to the rotor. The supply frequency is F. So therefore the frequency on the rotor is F, and the number of poles which are induced on the rotor is P, and same poles are going to be induced on the stator also, which is P. And let me assume this is the speed which is the rotor which is going to rotate. So this is the speed at which the rotor is going to get rotate. Then what is the frequency on the rotor is F, and the frequency in the frequency of the currents in the stator is F dash is equal to S into F, where S is the slip and F is the frequency in the rotor, and N is the speed of the rotor, and Ns is the synchronous speed with respect to rotor. So Ns is the synchronous speed with respect to rotor. Because we are going to give frequency to the winding on the armature, it is going to provide some flux. So Ns is the speed of the RMF, which is with respect to rotor. So Ns is the speed with respect to rotor. So therefore Ns is the speed with respect to rotor. So Ns is the synchronous speed with respect to rotor, and this is the rotor speed direction we are going to assume. So now we will discuss something more about this one. So stator RMF and the rotor RMF with respect to stator, which is ns minus n, ns minus n, because I already told you one important point, which is, so let me discuss the one important point here. See, this is the rotor speed. So this is the rotor speed. The rotor is rotating in this anti-clockwise direction. So this is the rotor speed. Suppose if I am standing on this rotor and I am seeing upward, then the speed of the RMF, the stator RMF, the rotor RMF or the stator RMF with respect to me is ns. So it is moving in the clockwise and I am moving in the anti-clockwise. See, the rotor is moving in the anti-clockwise and the speed of the stator RMF or the rotor RMF with respect to me on the rotor, which is ns. So this is the important point that you always have to remember, which is here the n is the speed, the nr is the speed, or nr is the speed of the rotor in this direction, which is called as the anti-clockwise direction. And if I stand on this rotor and if I see upward, the direction of the stator RMF or rotor RMF with respect to me standing on the rotor is ns in the clockwise direction. So this is the point that you always have to remember. So now stator RMF and the rotor RMF with respect to stator, which is ns minus n. So ns minus n is the ns minus nr, or we can say ns minus n or ns minus nr is the stator RMF and the rotor RMF with respect to stator, which is ns minus nr. It is always in the clockwise direction. It is always in the clockwise direction. So therefore, because always nr is always greater than nr, so because of that only it is always clockwise direction. So therefore, we can say very simple. So listen, you can get this formula by using some easy simplification, which is the speed of stator RMF with respect to me is on the rotor is equal to speed of rotating the stator RMF with respect to stator minus speed of rotor with respect to ground or stator. So listen carefully, the speed of stator RMF, or we can say rotor RMF with respect to me is on the rotor is equal to the speed of stator RMF or rotor RMF with respect to stator minus speed of rotor with respect to stator. As I am going to assume clockwise as positive and the anti-clockwise as negative, so therefore the speed of stator or rotor RMF with respect to rotor is nothing but ns in the clockwise is equal to, then this is this equation we want, which is called as the speed of stator RMF or rotor RMF with respect to stator minus speed of rotor with respect to stator, which is in the anti-clockwise, so minus n, because clockwise I am assuming positive, so anti-clockwise is negative. So negative is nothing but plus. If I take to LHS, we are going to get minus n. So therefore, ns minus n is called as the speed of stator RMF or the rotor RMF with respect to stator. So therefore, this is the important thing that you always have to remember. I have assumed clockwise as positive and the anti-clockwise as negative. So therefore, speed of stator RMF and the rotor RMF with respect to stator is nothing but ns minus nr. It is always in the clockwise direction. So always the rotor is going to rotate in the anti-clockwise direction. And if I stand on this rotor and if I see upward, the stator RMF or rotor RMF is rotating in the clockwise with respect to me when I am standing on this rotor. It is opposite to me. So therefore, it is opposite to the rotation of this rotor. Speed of stator RMF and the rotor RMF with respect to rotor. The speed of stator RMF and the rotor RMF with respect to rotor is ns. I have already told this point. The speed of stator RMF and the rotor RMF with respect to rotor is ns. It is opposite direction of the rotor rotation with respect to me and rotor. So it is always moving with the opposite direction of rotor rotation with respect to me and rotor. Suppose if the rotor is moving in the anti-clockwise, then definitely the ns is going to rotate in the clockwise. So speed of stator RMF on the rotor RMF with respect to rotor is ns. It is opposite direction of the rotor rotation with respect to me and rotor. So if I stand on the rotor, let me assume the rotor is rotating in the anti-clockwise. Then if I look up, then the speed of the stator RMF or the rotor RMF with respect to me on the stator is ns. So this is the point that you always have to remember. So finally, I can say that the speed of the stator RMF and the rotor RMF with respect to rotor is nothing but ns, and its direction is always opposite direction of the rotor rotation with respect to me on rotor. If I assume rotor is rotating in the anti-clockwise, then if I stand on the rotor and if I look upward, then the speed of stator RMF and the rotor RMF is going to move in the clockwise direction because it is opposite to the rotation of the rotor speed of stator RMF and the rotor RMF with respect to stator is nothing but ns minus nr. It is in the clockwise direction. It is in the clockwise direction. So now ns minus nr is equal to 120 f by p. See, I have already told you. See here, simply you can apply this important concept, which is here f dash is called as one important point. F dash is the frequency in the stator. So f dash is the frequency in the stator. So ns minus n is nothing but it is a stator RMF and the rotor RMF with respect to stator. So with this speed, the stator RMF or the rotor RMF is going to cut the windings in the stator. So with this speed, the stator RMF or the rotor RMF is going to cut the lines with this flux. So therefore, this is the speed in which they are going to cut the lines in the stator coils. So listen carefully. Ns minus nr is nothing but this is the speed of the stator RMF and the rotor RMF with respect to stator. So with this speed, they are going to cut the flux of the lines in the stator. So ns minus nr is equal to 120 f by p. Here f is nothing but f dash, because this is the frequency we are going to get induced in the coils of the stator. So this is the speed of RMF with respect to stator. So this is the speed of rotating magnetic field with respect to stator. So now you can get easily a value of f dash. Then what is the f dash is equal to s into f. So we can easily get, this is the relation, f dash is s is equal to f dash by f, or f dash is equal to s into f, and ns is called as the 120 f by p. So ns is nothing but 120 f by p. Here ns is equal to 120 f by p. It's a very important formula. So ns is equal to 120 f by p. F is the frequency which is given to the rotor, and by p is the number of poles which are induced on the rotor or stator. Always the number of poles induced on the rotor should be equal to number of poles induced on the stator. So this is the point that you always have to remember. So ns is equal to 120 f by p. It is a speed of the synchronous speed. It is synchronous speed with respect to rotor, or we can say that it is the speed of the stator RMF or the rotor RMF with respect to rotor. It is called as the ns. It is the opposite direction of the rotor rotation with respect to me on the rotor. Let me revise this concept again so that you can easily understand it. So inverted induction motor means I am going to give supply to the rotor coils. So if I give a frequency to the rotor coils, and let me assume the rotor is rotating in the anti-clockwise direction with the speed of nr or n. So the frequency given to rotor is f, and the number of poles induced on the rotor is p. Same number of poles are also going to induced on the stator. If the f is the frequency on the rotor, then f dash is the frequency on the stator, which is f dash is equal to s into f. So yes, we need to figure out. So now, as the rotor is rotating in the anti-clockwise, then the speed of the stator RMF or the rotor RMF with respect to rotor is nothing but it is in the clockwise direction. It is always opposite to the direction of the rotor. So it is in the clockwise direction with the speed of ns with respect to rotor. So whereas the stator RMF, or we can say speed of stator RMF or the rotor RMF with respect to stator is nothing but ns minus nr, or simply s into ns. It is in the clockwise direction. It is always in the clockwise direction. I have already told this concept, which is speed of stator RMF or rotor RMF with respect to me on rotor is equal to, see, the speed of stator RMF or rotor RMF with respect to rotor is equal to speed of stator RMF or rotor RMF with respect to stator minus speed of rotor with respect to stator. I have already told you I am assuming clockwise as positive and anti-clockwise as negative. So clockwise, so is equal to, here we are going to get ns is equal to, this is what we need, minus nr. So minus of minus nr is plus nr. If it goes to this side, we are going to get ns minus nr is equal to the speed of the stator RMF or rotor RMF with respect to stator. So clockwise we are going to get. So speed of stator RMF or rotor RMF with respect to stator is ns minus nr, which is in the clockwise direction, and the speed of stator RMF or rotor RMF with respect to rotor is ns. It is always opposite direction of rotor rotation with respect to me on rotor. It is always opposite direction of rotor rotation with respect to me on rotor. If I stand on the rotor is moving in this anti-clockwise direction with speed of n with respect to some stationary reference. And if I see upward, the stator RMF or rotor RMF with respect to me standing on rotor is nothing but ns. It is always in the quite opposite direction of the rotor with respect to me on rotor. Then the speed of stator RMF or rotor RMF with respect to stator. So with this speed, which is ns minus n is the nr is the speed. With this speed, the flux is going to cut the coils of the stator. So therefore, is equal to 120. The frequency of the currents in the stator coils is f dash by p. So now this is called the speed of RMF with respect to stator, or rotor RMF or stator RMF with respect to stator. I have already told you F dash is equal to S into F and NS is equal to 120 F by P. And F is the frequency given to the rotor coils, and P is the number of poles induced in the rotor or stator, both are always equal, and NS is the speed of the stator RMF or rotor RMF with respect to rotor. It is quite opposite direction of the rotor rotation with respect to me and rotor. So now we are going to study one important concept which is called as a single phase induction motor. So single phase induction motor, up to now we have studied about the three phase, but now we are going to study about the single phase induction motor in a very detailed manner. So you can see clearly here, it's a three phase winding of the stator, phase A, phase B and phase A. So you can see clearly here we are going to use the fuses, but suddenly one of the fuse was blown off. So one of the fuse was blown off. Then we can say as it is blown off, it's open circuit, so current will never enter inside this phase. So this coil is left alone because the current inside itself is equal to 0. So what only these two coils will have current. So current will pass from here and to here to here. So we can see only these two coils will have the current, but you see clearly these two are nothing but series combination because current here itself is equal to 0. So whatever the current here, same current is going to get flow. So now I am going to redraw this circuit which is equal to A and C. These two coils are now connected in series. If you do the addition of these two coils, you are going to get one coil. So we can say it is nothing but a single phase. We are going to give only a single phase supply. So therefore simply we can say it is if one of the fuses is blown off, then this three phase induction motor is equal to single phase induction motor. So now we will do further beautiful analysis of this concept. So you can say clearly this is the induction motor. So now this is only one coil. So we are going to wound only one coil to the stator. And so one coil means there are two terminals. So these two terminals I am going to give one single phase supply. Will I get a rotating field or not? Yes, definitely you are going to get the rotating magnetic field, but its strength is not very high when its strength is very less. So here E2, I2 and T produced in the rotor. EMF induced in the rotor, I2 is the current induced in the rotor, and torque is developed on the rotor. These three are going to produce in the rotor, but still not rotating. See, this E2 EMF is going to induce in the rotor, current is also going to induce in the rotor, torque is also produced in the rotor, but still it is not rotating because this torque was cancelled out, but this rotor rotates in the direction in which you rotate, anti-clockwise and clockwise. This was explained by Ferrari with double revolving field theory. So what is going to happen, even though you are going to use single phase supply, the rotor is going to have the induced rotor voltage, induced rotor current, and torque is also going to get developed in the rotor, but still the rotor is not at all going to rotate. But if you give a initial starting, if you rotate with your hand in the clockwise and anti-clockwise, it is going to start its rotation in the way in which you are rotating. Suppose if you rotate with your hand in the clockwise, then it is going to start to rotate in the clockwise direction. But if you want to rotate in the anti-clockwise, it is going to start rotating in the anti-clockwise direction. So this is the called as the, see, it is not a self-starting motor. You have to start it. You have to give the starting, then only it is going to get rotor. It is not a self-starting motor. So single phase induction motor is not a self-starting motor. So why it is not starting? This was the concept behind it. Why even the torque is producing, why it is not rotating? This concept was explained by the Ferrari with its double revolving field theory. So E2, I2 and T, EMF induced in the rotor, current is also induced in the rotor, torque is also produced in the rotor, even if you give the single phase supply, but still it is not rotating because this torque was cancelled out. But this rotor rotates in the direction in which you rotate. If you rotate in the anti-clockwise, it is going to rotate in the anti-clockwise. And if you rotate in the clockwise, it is going to rotate in the clockwise. Why this is happening? This concept was explained by the Ferrari with its double revolving field theory. So now we understand this field theory. Why initially it is not rotating, even the torque is produced. Why this torque was cancelled out? This we are going to learn through this concept of double revolving field theory, which was explained by the Ferrari. Double revolving field theory. So double revolving field theory we are going to study now. See here the flux phi m, whatever the flux phi m which is produced in the air gap between the stator and the rotor, we are going to make it into two parts. One is the forward field and the other is the backward field. We are going to split into two parts. One is called as the forward field and the other is called as the backward field. So whatever the flux which is produced in the rotor between the stator and the rotor, we are going to split into two parts. One is called as the forward field and the other is called as the backward field with of equal magnitude. If phi m is the overall flux produced, then phi m by 2 is for the forward field and phi m by 2 for the backward field. So forward it is going to rotate with the speed of ns and the backward it is going to rotate with the speed of ns. So therefore we can say ns is the field, ns is the speed at which the forward field is going to rotate, and ns is the speed in which the backward field is going to rotate. So both are of same speed nature but of different directions. So whatever the flux produced between the stator and the rotor, the overall flux is phi m. So we are going to split into two parts. One is forward field and the other is backward field. The forward field is going to rotate with the speed of ns and the backward field is also going to rotate with the speed of ns. So let me assume I am giving an initial. Manually I am going to rotate the rotor in the clockwise. This is what I am going to assume. After that it is going to rotate with the speed of n or n. Then what is the forward slip? As the forward field and the rotation of the rotor are in the same direction, so we can say that the resultant we can say the relative speed is ns minus nr by ns. So forward slip is equal to ns minus nr by ns. But I want to know what is the backward slip. If this is rotating in the clockwise and this is the anti-clockwise, both are of opposite nature, so we can say the resultant speed is ns plus nr. So therefore the backward slip is equal to ns plus nr by ns. I wanted to told this one add plus ns and minus ns. If you do the simplification, finally we are going to get 2 minus sf. So backward slip is always equal to 2 minus forward slip. So backward slip is always equal to 2 minus forward slip. So backward slip is always equal to 2 minus forward slip. So backward slip is always equal to 2 minus forward slip. So this is the concept that we need to always understand. So during starting or standstill condition, the rotor speed is equal to 0. So whenever the rotor speed is equal to 0, then forward slip is equal to 1. If you substitute forward slip is equal to 1, we are going to get backward slip is also equal to 1. During running condition, let me assume at no load condition, the rotor speed is nearly equal to synchronous speed, then definitely the forward slip will be equal to 0. So if you substitute here sf is equal to 0, the backward slip we are going to get 2. So these are the important things that you always have to understand. So now, what is the forward torque? So forward torque is equal to 60 by 2 pi ns into rotor copper loss by sf. I have already told you power is equal to torque into omega. So torque is equal to power by omega. So rotor power input by omega. So omega is equal to 2 pi ns by 60. Rotor power input is nothing but rotor copper loss by sf. Because we are going to use the forward torque means we have to use the forward slip. Suppose if you want backward torque, then you have to use the backward slip, which is TB is equal to 60 by 2 pi ns into rotor copper loss by backward slip. So during starting, what is going to happen? I have already told you during starting. So during starting, n is equal to 0. So therefore nr is equal to 0. So sf is equal to 1 and sb is also equal to 1. So during starting, the forward torque is always equal to backward torque. So because of this only we can say that it is not at all moving. So at starting, the forward torque is always equal to backward torque. So because of that it is not at all rotating. That is the concept behind it, why it is not rotating. It is not a self-starting. But if you give an initial way of rotation, it is going to rotate permanently in that direction. That is the concept that you need to always understand. So you can see clearly during starting, nr is equal to 0, so sf is equal to 1 and sb is equal to 1. If you substitute sf is equal to 1 and sb is equal to 1, you can see both the expressions are equal. So forward torque is equal to backward torque. So that is the result, it is not rotating at the initial condition. So now I am going to draw the characteristics of the forward torque and the backward torque on this rotor we are going to draw. So therefore, this is the graph with respect to forward torque, and this is the torque with respect to the backward torque. So you can see clearly at s is equal to 1. At s is equal to 1 is nothing but simply this is a positive means this is a negative. So both are of opposite nature. So if this is plus 1 and this is minus 1, at starting means I have already told you s is equal to 1 and sb is also equal to 1. So therefore at s is equal to 1, it is called as the starting condition. So therefore the forward slip magnitude and the backward slip magnitude are same. One is positive, other is negative. So overall value is equal to 0. So therefore we can say that we are going to get a 0. This is called as the actual torque. So actual torque is the addition of the forward torque and the backward torque. So if you do the addition of these two graphs, we are going to get the resultant torque, or we can say actual torque we are going to get. This is the, see, from s is equal to 0 to s is equal to 1 and s is equal to 1 to s is equal to 2 also you are going to get. This is the forward torque. We can say torque of positive value and torque of negative value we are going to get. So actual torque is also called as the overall torque. So this is the overall torque diagram of a single phase induction motor. So therefore at s is equal to 0, the resultant torque is also equal to 0, and s is equal to 1 also, the resultant torque is also equal to 0. So this is the beautiness of this one, of single phase induction motor. But this is not the case in a 3-phase induction motor. At s is equal to 0, torque is equal to 0, but s is equal to 1, torque is not at all 0 in a 3-phase induction motor. But in a single phase induction motor, at both these cases the torque is always equal to 0. But here it is a positive nature and here it is a negative nature. So this is a point that you always have to remember for your lifetime whenever you are living in this planet Earth. So therefore s is equal to 1 to s is equal to 2, it is called the braking region and here it is called the motoring region. So this is the overall actual torque, or the overall torque which is produced on the single phase induction motor. So now we will see some important formulas. Ns is called as the 120F by P, and forward slip is equal to Ns minus Nr by Ns, and the backward slip is equal to 2 minus Sf. Sf is called as the forward slip, and Sb is called as the backward slip, and Tf is called as the forward torque, and Tb is called as the backward torque. These are the important notations that you always have to understand for your lifetime. So therefore Ns is equal to 120F by P, and Sf is equal to Ns minus Nr by Ns, and Sb is equal to 2 minus Sf, and Sf is called as the forward slip, and Sb is called as the backward slip, and Tf is called as the forward torque, and Tb is called as the backward torque. So Tf is called as the forward torque and Tb is called as the backward torque. So at the initial condition, or we can say at the starting condition, the forward torque is equal to backward torque. So because of that, overall torque produced on the rotor at the starting is always equal to 0. So that is the reason it is not rotating. So it is not a self-starting motor. You have to give some initial manual way of rotating, then it is going to rotate in the direction which you are rotating it. That is, this concept was explained by the Ferrari with his double revolving field theory. So I hope you have understood this concept. So now we will move forward to understand remaining concepts. So now we are going to understand what is the equivalent circuit diagram of a single phase induction motor. The equivalent circuit diagram of a single phase induction motor. So I have given the basic idea of a single phase induction motor, but now we have to draw the diagram, equivalent circuit diagram of single phase induction motor. So this is the equivalent circuit diagram of a single phase induction motor. So this is the rotor, or we can say stator resistance, and this is the we can say it is said to be stator reactance, leakage reactance, and with a single phase means we have to give only one voltage. So therefore this is the we can say it is the single phase voltage. So now here we are going to draw with respect to stator. So we are going to draw with respect to stator. So you can see clearly this is RC by 2, this is also RC by 2, this is XM by 2, and this is XM by 2 in this parallel. And here we are going to take into another format which is called as the R2 dash by 2SF, X2 dash by 2, R2 dash by 2 into SB, and X2 dash by 2. So this is with respect to forward rotation and this is with respect to backward rotation. I have already told one important point here, S into E2, here R2, here S into X2. So now divide by S on all the three sides, we are going to get E2, R2 by S and X2. So R2 by S we need to do here. But I am going to split R2 into two parts, one is above and one is down. So this is R2 by 2, here X2 by 2. Here R2 dash by 2, here X2 dash by 2. Here RC by 2, RC by 2, XM by 2, XM by 2. Just use the SF for resistor and SB for resistor here. So this is for the forward rotation and this is for the backward rotation. So this is the voltage V, R1, X1, RC by 2, RC by 2, XM by 2, XM by 2, R2 dash by 2, XM dash by 2, R dash by 2, X2 dash by 2. But for resistor use denominator SF here and use here SB here. So this is the important way that you always have to remember for your lifetime. So this was supply voltage V, R1, X1, RC by 2, RC by 2, XM by 2, XM by 2, and this is R2 dash by 2, X2 dash by 2, R dash by 2, and X2 dash by 2. This is here SF, here SB for the forward rotation and this is for the backward rotation. So SF is, let me assume SF is equal to S, the forward slip is equal to S, so backward slip is equal to 2 minus SF which is equal to 2 minus S. So simple notation is like this. So now we are going to further do some more analysis. So we try to do some approximations. So therefore the circuit seems to be very easier, or we can say very simpler to analyze. As I've already told you, the RC is very huge value. So we are going to neglect it because it's a very huge value. So we are going to open circuit that part. So RC is very huge. So we are going to neglect that part. And remaining things we are going to consider. So listen here. This is R1, X1. This is Xn by 2, Xn by 2. R dash by 2, S dash by 2. R dash by 2, L dash by 2. Here forward slip means I have assumed SF means S. The backward slip means here SB. SB means 2 minus SF. SF is nothing but S. So 2 minus S. So this is the thing that you always have to remember. So now what is the, I am going to do the analysis of this circuit. So let me ask you, this is Z1. Z1 is equal to R1 plus JX1. Then what is the ZF? For the forward rotation, the impedance with respect to forward rotation, ZF is equal to here J into Xm by 2 with the parallel combination of this is series combination, which is R dash by 2S plus J into S dash by 2. So I am going to try to find what is the equivalent impedance of this forward rotation. And now finally, if you do a simplification, we are going to get RF plus JXF. And ZB is called as a backward rotation equivalent impedance, which is J into Xm by 2, the parallel combination of R dash by 2 into 2 minus S plus J into X dash by 2. So if you solve this one, we are going to get RB plus JXB. So finally, we are going to simplify this one, which is R1 X1, this is RF, this is XF, this is RB, this is XB. So now, like this we are going to get, this is supply voltage B and this is supply current I. So what we are going to get, what is the efficiency? Efficiency is called as the output by input. So efficiency is nothing but output by input. So what is the output, which is called as the, see, basically output is nothing but the shaft output power, shaft output by input power is nothing but here you can see clearly input power is V into I into cos phi, where phi is the phase angle between the supply voltage and supply current. So therefore, efficiency is equal to output by input. Output is nothing but shaft power by input is called as the V into I into cos phi, because it is a single phase supply. So V into I into cos phi, where phi is the power factor angle between the supply voltage and supply current. You can see clearly it has a resistor and inductor. So basically it is said to be a inductive circuit. So what is the torque? So I want to find what is the expression of the torque. So torque is nothing but very simple, which is called as the expression of the torque is very simple, which is equal to P is equal to T into omega. So T is equal to P by omega. So T is equal to P, which is called as the rotor power input. Rotor power input by omega. Omega is 2 pi ns by 60. So like this you are going to get T is equal to 60 by 2 pi ns into rotor power input. So this is the expression of the torque. So power is equal to torque into omega. So torque is equal to power by omega. So torque is equal to rotor power input by omega. Omega is equal to 2 pi ns by 60. Means it is, after arranging we are going to get torque is equal to 60 by 2 pi ns into rotor power input. Then this is the, we can say, general expression. So for forward torque is nothing but 60 by 2 pi ns into forward power input. Similarly, for backward torque is equal to 60 by 2 pi ns into backward power input. So backward power rotor power input, or you can say forward rotor power input, backward rotor power input. So this is a very important. So TF is equal to 60 by 2 pi ns into PF is called as the forward rotor power input. TV is equal to 60 by 2 pi ns into backward rotor power input. So now you will see something more about this one. So what is the supply current? I is equal to supply voltage by, this is called as the Z1, this is called as the ZF, and this is called as the ZB. So therefore V by Z1 will ZF plus ZB. So after solving this one, we are going to get magnitude of current into at an angle of minus phi, because I have taken the voltage as a reference phasor, then the lagging circuit current is going to always lag. So phi is called as the operating power factor angle. It is always lagging because the circuit is always lagging circuit. So therefore phi is called as the operating power factor angle and it is always lagging in nature. What is the active power input to motor? So what is the active power input to motor? So active power input to motor is nothing but, see, what is the active power input to motor? It is a single phase supply, so V into I into cos phi. The active power input to motor is nothing but, which is V into I into cos phi. And the rotor power input is equal to, so rotor power input is equal to, so what is the rotor power input? So rotor power input is, what is the expression? So rotor power input means PF. PF is called as the forward rotor power input, but generally we need the rotor power input. So I have already told you rotor power input is nothing but I2 dash whole square into R2 by S. this is the general expression. This is the general expression. So rotor power input is equal to I2 dash whole square into R2 by S. So therefore we can say that the rotor power input is equal to I2 dash whole square into R2 by S. This is the general expression. So rotor power input is equal to I2 dash whole square into R2 by S. So the rotor power input, so we can say the rotor power input general expression is I2 dash whole square into R2 by S. Then what is the S into rotor power input? S into rotor power input is called the rotor copper loss. So rotor copper loss is I2 dash whole square into R2. So listen carefully, very important point. So very important point. So what is the rotor copper loss? I have already told you, rotor copper loss is nothing but I2 dash whole square into R2. Then what is the rotor? See, rotor copper loss is equal to I2 dash whole square into R2. Then what is the rotor power input, which is rotor copper loss by S. So rotor copper loss by S, we are going to get rotor power input. So this is the thing that you always have to remember. So rotor copper loss general expression is I dash whole square into R2, whereas rotor power input is equal to rotor copper loss by S, which is I dash whole square into R2 by S. So PF is called as the power input to forward rotor direction. So and you can say rotor power input to forward rotor direction, which is I square into RF, because I square into RF. So I square into RF is called as the power input to forward rotor direction, and PB is called as the power input to backward rotor direction, which is I square into RB. So therefore we can say power input to forward rotor direction is equal to I square into RF, whereas the power input to backward rotor direction is equal to I square into RB. So now net power input to rotor is forward minus backward. So net power input to rotor is forward minus backward. So therefore this is the thing that you always have to remember. So I square into RF is called as the PF, which is power input to forward rotor input, and I square into RB is called as the PV, which is power input to backward rotor direction. So now PF minus PB is called as the net power input to the rotor. So PF is called as the power input to forward rotor direction, which is equal to I square RF, and PB is called as the power input to backward rotor direction, is equal to I square into RB. Then what is the net power input to rotor, which is PF minus PB? So power output of rotor. So what is the power output of rotor? I have already told you, power output of rotor is nothing but 1 minus S into net power input to rotor, which is 1 minus S into PF minus PB. So power output of rotor is nothing but 1 minus S into rotor power input, which is 1 minus S into PF minus PB in this case. Then what is the shaft output? The shaft output is nothing but shaft output power is equal to rotor power output minus some constant losses or rotational losses. So if you remove the losses from this one, we are going to get the shaft output power. So shaft output power is equal to power output of rotor minus constant losses, or we can also call it as a rotational losses or mechanical losses. Basically we can simply call it as a mechanical losses. In general case we call it as a mechanical losses. So therefore shaft output is equal to PSH is equal to power output of rotor, which is PF minus PB into 1 minus S minus mechanical losses. Here we have to use the mechanical losses. Then this is called as the shaft output power. I have already told you TF and TB expressions. Now do the subtraction of the TF minus TB. If you do the subtraction of TF minus TB, you are going to get one important point, which is called as the 60 by 2 pi ns into PF minus PB. So PF minus PB, so we are going to get, let me assume this is called as the, so therefore shaft torque. So therefore finally we can say the total torque is nothing but TF minus TB is equal to TSH. TSH is equal to, so therefore the total torque is nothing but shaft torque is equal to TF minus TB is equal to shaft torque is equal to 60 by 2 pi NR into PSH. So therefore 2 pi NR into 60 by 2 pi NR into PSH. So this is called as the Newton per meter. So this is the shaft torque. Shaft torque is nothing but forward torque minus backward torque. You are going to get the shaft torque, which is 60 by 2 pi N into PSH. So shaft power. So now we are going to discuss about the determination of equivalent circuit parameters of single phase induction motor. So we have drawn the equivalent circuit diagram of a single phase induction motor. Now we need to figure out these parameters with the help of doing some tests. So determination of equivalent circuit parameters of single phase induction motor. By performing some tests, we are going to figure out the parameters of the single phase induction motor. So it is called as determination of equivalent circuit parameters of single phase induction motor by performing few tests. The first test that we are going to perform is called as the no load test. So no load test that we are going to perform on the single phase induction motor. So you can see clearly here, it is a single phase auto transformer. So it's a single phase auto transformer means we can vary the supply voltage to the terminals of the single phase induction motor. So it is a single phase auto transformer. The supply voltage we can measure with the keeping a voltmeter across these two terminals, and see, as it is a no load test, let me assume the notation is VNL. And the current is taken by the stator at this no load condition. The current is INL, which we can measure with the keeping an ammeter, and also we are going to keep a wattmeter. As it is a single phase supply, we need only one wattmeter to measure the amount of power which is taken by this. But if it is a three phase, we have to use the 2 wattmeter method, but it is a single phase, so we can only use 1 wattmeter to measure the how much amount of power which is absorbed by this induction single phase induction motor. See, as we are not going to keep any load, as it is a no load test, as it's a no load test, we can say that the rotor speed is nearly equal to synchronous speed. So therefore the slip is nothing but 0. So whenever the slip is equal to 0, I've already told, then we can say what is the shaft power. As I can say that simply slip is equal to 0. I've already told what is the torque produced. Torque produced also equal to 0. The electromagnetic torque produced is equal to 0. As electromagnetic torque is equal to 0, what is the shaft output power is also equal to 0, because we are not using any power to the outward load. So we can say shaft power is also equal to 0, because as slip is equal to 0, the torque is also equal to 0. So therefore the shaft output power is also equal to 0. So at the no load condition, even though we are not going to keep any load, a small amount of power is taken by the single phase induction motor. That input power is going to be used by some losses. So it is wasting in the losses, because the output itself is equal to 0. And we will see what is the losses. See, I have already told you input is equal to output plus losses. And the output is equal to 0. So input should be always equal to losses. Now we are going to see what are the losses which are going to present in this single phase induction motor. So in the stator there will be 2 losses, which is stator copper loss and stator core loss. In the rotor also there will be 2 losses, which is rotor copper loss and rotor core loss. And finally we are going to get the mechanical losses, or simply we can also call it as the friction and windage losses. But now at no load test, as the slip is equal to 0, the rotor core loss is also equal to 0. The rotor core loss is also equal to 0, but we are going to reduce. See, the rotor copper loss is equal to 0. So the rotor core loss is also very, very low. We are going to neglect this one. So therefore, the rotor copper loss is equal to 0 and the rotor core loss are also equal to 0. We are going to neglect these 2 terms. And now we are going to get with only 3 types of losses, which is stator copper loss, stator core loss, and the mechanical losses. So the total input power is nothing but which is measured by the wattmeter. So WNL is equal to stator copper loss, stator core loss, and mechanical losses. If I take the stator copper loss to the left hand side, which is WNL minus stator copper loss is equal to stator core loss plus mechanical loss. See, always stator core loss plus mechanical loss is always said to be a constant losses. So therefore WNL minus here INL square into R1, because INL is the current which is drawn by this one, then R1 is the stator copper loss, where R1 is the resistance of the stator, so therefore stator winding, so therefore INL square into R1 is called as the stator copper loss. So WNL minus INL square into R1 is called as it is called as the constant losses. So now I am going to redraw this equivalent circuit diagram, so you can see clearly what is going to happen. As the equivalent circuit, see, I am going to neglect that RC part, because RC part is very huge. We are going to already neglect it. So this is called as it is a single phase. So VNL and this is INL, R1 X1 here, X1 by 2, X1 by 2 here. I have already told this is called as the R2 dash by 2 into S. As S is equal to 0, we can say anything by 0 is equal to infinity. So we are going to neglect this part, because see here also S2 dash by 2, infinity plus some non-zero value is again infinity. So we are going to open circuit this one. Here we are going to get R2 dash by 2 into 2 minus S. As S is equal to 0, so 2 into 2 is called as a 4. So R2 dash by 4 and X2 dash by 2. So this is Xn by 2. So this is the circuit we are going to get from the original equivalent circuit. So therefore VNL is called as the rated voltage, because in open circuit voltage we have to give the rated voltage. This is called the rated no load voltage. And Xn by 2 is also very huge value. Xn by 2 is also very huge value. So we are going to neglect this one also. And S is always equal to 0 in case of no load test. I have already told one important point. See, no load test is similar in a transformer, is similar to here no load test in the induction motor also. This is a very important point that you always have to remember. The short circuit test in transformer is equal to block rotor test in the induction motor. So this is a point that you always have to remember. So now we will do further simplification of this circuit. So this is R1 X1. As I have already told, this is Xn by 2. Here what I am going to do basically, here Xn by 2 is a very huge value. So I am going to neglect this Xn by 2 here. So I am going to remove this one. So I am going to take only this part, which is R dash by 4 and S dash by 2. So this is for the forward rotor and this is for the backward rotor. So this is for the, this parameter is for the forward rotor and this is for the backward rotor. And now what is the total? Then XNL is nothing but X1 plus Xn by 2 plus X2 dash by 2. Then what is the RNL, which is equal to R1 plus R dash by 4. So this is the XNL, which is equal to X1 plus Xn by 2 plus X2 dash by 2, and RNL is equal to R1 plus R dash by 4. So this is the equivalent diagram we are going to get at this no load test for the single phase induction motor. So now we try to figure out these parameters with the help of this no load test from these meters. So from meters, what is ZNL is equal to VNL by INL. We know VNL, we know INL. If we do the division of these two values, we are going to get the ZNL. So from meter readings, ZNL is equal to VNL by INL, because we know VNL, we know INL. Just do the division of these two things, we are going to get the ZNL. Then WNL is equal to, I have already told you, INL square into RNL. So WNL is equal to INL square into RNL. So therefore RNL is equal to WNL by INL square. We know WNL, we know INL. Just do this ratio, we are going to get RNL. Then XNL is equal to under one ZNL whole square minus RNL whole square. So now with the help of these things, we know ZNL, we know RNL, and we know XNL. So RNL is known, XNL is also known from the help of this meter readings. So always forward rotor voltage drop, MMF, flux greater than the backward rotor voltage drop, MMF and flux. So this is a very important point. Always forward rotor voltage drop, MMF and flux are always greater than the backward rotor voltage drop, MMF and flux. And the peak of forward stator MMF is equal to the peak of the backward stator MMF. So this is a very important point. Always the forward rotor voltage drop, MMF and flux are always greater than the backward rotor voltage drop, MMF and flux. Whereas the peak of forward rotor stator MMF is equal to peak of the backward stator MMF. So this is a very important point. Peak of the forward stator MMF is always equal to peak of the backward stator MMF. These 2 points that you always have to remember for your lifetime, which is always forward rotor voltage drop and the MMF and the flux is always greater than the backward rotor voltage drop, MMF and flux. Whereas the peak value of the forward stator MMF is always equal to peak value of the backward stator MMF. So always forward rotor voltage drop, MMF and the flux are always greater than the backward rotor voltage drop, MMF and flux. Whereas the peak value of the forward stator MMF is always equal to peak value of the backward stator MMF. So with the help of no load test, we can figure out some of the parameters of the equivalent circuit diagram of a single phase induction motor. Now we are going to perform another test, which is called as the block rotor test. So block rotor test, with the help of this we are going to find the remaining parameters of the single phase induction motor. So here single phase auto transformer we are going to give, this is the VDR. With the help of voltmeter we are going to measure the supply voltage. See, it's a very less amount of voltage to get the required amount of rated current. This is ammeter. With the help of this we are going to get the IBR, and with the help of voltmeter we are going to measure how much amount of power is taken by the single phase induction motor. So here we are going to block it. It is not at all going to, it is not going to rotate. So NR is equal to 0. As NR is equal to 0, the forward slip is equal to 1. So therefore As forward slip is equal to 1, we are going to get. So it is called as the starting stage. It is also called as the starting stage. So definitely we are going to produce some torque. So now we will see some analysis regarding this one. As NR is equal to 0, so there will be no mechanical losses. So mechanical losses are blindly 0 because there is no rotation. So just we need only 5% of rated voltage to get the rated value of the current in this circuit. So with the help of these values, we are going to find the remaining parameters of the single phase induction motor. So input is equal to output plus losses. So this is the general concept. But output, see, we are not going to keep any useful load. So output is always equal to 0 because as output is equal to 0 because output power is nothing but torque into omega. As NR is equal to 0, so omega is equal to 0. So output power is also equal to 0. So now, so input power should be always equal to output power plus losses. As the output power itself is equal to 0, then definitely input power should be equal to losses. Input power is WBR, which is read by the wattmeter. So WBR is equal to losses. So what are the losses in a single phase induction motor, which is stator core loss? I've already told the different type of losses. Stator core loss, stator copper loss, rotor core loss, rotor copper loss, and mechanical losses. Now, as the rotor speed is equal to 0, so mechanical losses are 0. So we are going to neglect this one. And also one more important point here is the supply voltage is a very less value. It is only 5%. So therefore, the stator core loss are also neglected and the rotor core loss are also neglected because whenever the supply voltage increases, the core loss are going to get increased. As the supply voltage is a very less value, so we are going to neglect these two values. So stator core loss and the rotor core loss are neglected and the mechanical loss are 0 because the rotor speed is equal to 0. So now we are going to remain with stator copper loss and rotor copper loss. So we can say that what are the input which is absorbed by this stator copper loss and rotor copper loss. So therefore WBR is equal to input is equal to stator copper loss plus rotor copper loss. So now we are going to analyze the equivalent circuit diagram for this one. As I have already told you, this is the R1, this is the X1, this is the VBR, and this is the IBR. This is called as the IBR current. So this is basically IBR. So now, so this is IBR. So this is VBR and this is IBR. This is R1, X1. This I have already told you RC is very huge. So we are going to neglect RC by 2 and RC by 2 we are going to neglect. This is XM by 2, XM by 2. This is R2 dash by 2 into forward slip is S, as I see S is equal to 1, so we are going to keep here 2, and this is X2 dash by 2, and here R2 dash by 2 into backward slip is 2 minus forward slip, as forward slip is equal to 1, so backward slip is also equal to 1, so 2 into 1 is again 2, this is X2 dash by 2, as Xm by 2 is a very huge value, so we are going to neglect it, and S is equal to 1, S is nothing but forward slip. As I have already told you, Xm by 2 is a huge value, so we are going to neglect here, we are going to neglect here also. Both the things we are going to neglect. So this is VBR, here it is IBR, and this is R dash by 2, X2 dash by 2, and this is R dash by 2, and this is X2 dash by 2. So we can see clearly both are having the same impedance, so same voltage drop. So same voltage drop we are going to get here because here same impedance, so we are going to get same voltage drop for the forward rotor and the backward rotor. This is for the backward rotor and this is for the forward rotor. So therefore R dash by 2 plus R dash by 2 is nothing but R2 dash, and this is X2 dash by 2 plus X2 dash by 2 is nothing but X2 dash. So this is R1, X1, R dash and X2 dash, and this is VBR and this is IBR. So RBR is nothing but simply R1 plus R2 dash, and XBR is nothing but X1 plus X2 dash. So from meters we can say clearly from meters, then what is the value of ZBR is equal to VBR by IBR. So we know VBR, we know IBR, just to the ratio we are going to get ZBR. Then WBR is nothing but IBR square into RBR. So RBR is equal to WBR by IBR square. We know WBR and IBR. Just do this ratio we are going to get RBR. Then XBR is nothing but under root of ZBR whole square minus RBR whole square. So now we can get the XBR. So I have already told you XBR is equal to X1 plus X2 dash. We will assume X1 is nearly equal to X2 dash. So therefore X1 is nearly equal to X2 dash is nearly equal to XBR by 2. So by performing the no load test and the block rotor test, we can figure out the each and every parameter of the equivalent circuit diagram of a single phase induction motor. So this is the concept that you need to always understand here. So what happens if you give two-phase supply for an induction motor? So what is going to happen if you give two-phase supply for induction motor? So these things now we are going to study. So let me assume phi A is equal to phi m sin omega t and phi B is equal to phi m sin omega t minus 90. So phase difference is 90. It is said to be balanced two-phase supply. So balanced two-phase supply means the angle between them should be equal to 90 degree. So whenever the angle should be between them is 90 degree and both having the same magnitude, we say these are said to be balanced two-phase supply. So whenever the two-phase supply is given to induction motor, what is going to happen? So what is the net flux? Just to the addition of these two, phi A and phi B, we are going to get the maximum value of the net flux is nothing but phi m. So therefore, it is also rotating at the synchronous speed, which is 120 f by p. So even though you are going to give two-phase balance supply, still we are going to get a synchronous speed of rotating magnetic field of speed, which is ns is equal to 120 f by p, the revolutions per minute. And the maximum value of the net flux is again equal to phi m, whereas in the three-phase, which is 1.5 times the phi m. The peak value of the net flux in the three-phase is 1.5 times the phi m, whereas here it is equal to phi m itself. If you try to analyze the graph between the torque and the speed, then we can see for the three-phase supply, two-phase supply and one-phase supply. This is for the single-phase induction motor, two-phase induction motor and a three-phase induction motor. Basically, we can say it is basically a single-phase induction motor, two-phase induction motor or three-phase induction motor. So for a single-phase induction motor, I have already told you here at n is equal to nr, nr is equal to ns and nr is equal to 0, we are going to get 0 torque. So we are going to get in this format. This is for the two-phase induction motor or two-phase supply when it is given, and this is for the three-phase induction motor or three-phase supply we are given. So we can see clearly for a single-phase induction motor at nr is equal to ns and nr is equal to 0, we are going to get 0 torque. Whereas here this is for the two-phase induction motor and this is for the three-phase induction motor. So always three-phase induction motor, as for each and every rotor speed, we are going to get more amount of torque is produced, but still the synchronous speed is same and the speed is very same for each and every case. But the only thing is the amount of torque produced at each and every speed is very higher for three-phase when compared to two-phase when compared to single-phase. Anyhow, the speed of the rotating magnetic field is same in all the three cases, but only thing is at each and every speed the amount of torque produced in case of three-phase induction motor is higher when compared to two-phase and when compared to single-phase. And here this is the point that you always have to remember: at nr is equal to ns and nr is equal to 0, always the torque is equal to 0 for a single phase induction motor. That is the reason it is said to be it is not a self-starting motor. Whereas the two phase and single phase are self-starting, because even though nr is equal to 0, torque is produced, so it can rotate. But here torque is also equal to 0. That is the reason it is said to be we can say it is said to be a not self-starting motor. Only single phase induction motor is not self-starting, whereas the two phase and three phase are self-starting motors. So now we are going to discuss which is called as the split phase or the resistance split phase induction motor. It is basically a single phase induction motor. Split phase or resistance split phase single phase induction motor we are going to study in a very detailed manner. So this is called as the main winding and this is called as the auxiliary winding. So this is called as the main winding and this is called as the auxiliary winding, or we can call this as the running winding and this as the starting winding. So this is used only for the starting purpose, so it is called as the starting winding, and this is used for the running purpose, so it is called as the running winding. So for the starting purpose we need huge amount of starting torque, so therefore its resistance is very high and inductance is very less. Whereas here the reverse process, the resistance is very less and the inductance is very huge for this main winding. So Im is the current which is flowing in this main winding, and Ia or Is, you can go for any of these, the current in this auxiliary winding. So here we are going to use some certain type of centrifugal switch. So therefore this switch is going to get open after the rotor has reached certain amount of speed. So therefore now this is called as single phase AC supply. So this M is called as the main winding and A is called as the auxiliary winding. I have already told you its resistance is it's a highly resistive, so inductance is very less. Whereas main winding has the less amount of resistance but huge magnetizing reactance. AC is called a centrifugal switch. Centrifugal switch means the switch is going to open only after reaching certain amount of speed by this rotor. So based on the speed, it is going to operate the switch. So it is called as a centrifugal switch. Where R is called as the squirrel cage rotor. This is basically a squirrel cage rotor. So now if Im is called as the main winding current and Is is called as the starting winding current, or simply we can call auxiliary winding current, because this is used for the starting purpose, so it is called as the starting winding, and this is used for the running purpose, so it is also called as a running winding. So if I draw the phasor diagram, this is the supply voltage V, and I already told you this is highly resistive. So this is highly resistive means, so we can say the current is going to, here IS current you are going to get less lagging, whereas this is highly magnetizing current, so therefore this is highly magnetizing reactance, so more amount of lagging, so less resistive and more inductive, so it is going to lag more, so therefore this is the IM current. So IS is going to lag lesser lag when compared to IM with respect to supply voltage. So more is the inductive, more is the lagging. Simply we can say like that. But alpha is the angle between these two currents, IS and the IM. So IS is going to produce the flux, IM is also going to produce the flux. So because of these two interaction of these fluxes, we are going to get a rotating magnetic field. So then this induction rotor, or we can say this rotor is going to get rotate. With the interaction of these two fluxes, it is going to get rotate. So we can say that here alpha is nearly equal to 30 degrees, it is enough to produce the RMF. If alpha is nearly equal to 30, it is enough. If it is more than that, it is very sufficient, but the minimum angle should be 30 degrees. If 30 is possible between these two phasors, then definitely we can say yes, the rotating magnetic field is produced in this air gap, so then this rotor can rotate. So we can say that simply it is said to be like this. So therefore this is used for starting purpose, so no need to manually, so no need to go for manual operation. Now we can easily go for this automatic operation. So alpha is nearly equal to 30 degrees is enough to produce the RMF. So this is the diagram when the switch is closed, because IS is also going to get flow, and the starting torque is directly proportional to here IM into IS into sine alpha, where alpha is the angle between these two, because IS is producing a flux, IM is also producing a flux, and alpha is the angle between these two fluxes. So IS is producing a certain flux, IM is also producing certain flux, and the angle between them is called as the alpha. So I have already told you 5 into 5 2 into sine the angle between them. So therefore here Tm into Ts into sine of alpha. Alpha is the angle between these two fluxes or two currents. So starting torque is directly proportional to Im into Is into sine alpha, where alpha should be nearly equal to 30 degrees. It is the minimum angle. If it is more than that, it is very good, but the minimum it should be 30 degrees. So therefore it is enough to produce the RMF. So now this rotor can rotate with we can say now it is can rotate. We can say now it is can rotate without any manual operation. So it can rotate automatically. So we can say this is called as a self-starting. Now it can self-start. You don't have to go for the manual operation to starting this one. So we are going to keep this one. So therefore it can provide the self-starting. Suppose when switch is open. So when switch is open means I can say that Is is equal to 0. Only Im is going to flow. So this is the Im current. I have already told you Im has huge amount of magnetizing reactance. So it is going to lag very higher when compared to Is. So therefore the angle between the supply voltage and supply current is called as the power factor angle. This is the phi whenever the switch is open. If I draw the characteristics between the torque and the speed. So if I draw the characteristics between the torque and the speed for the different one, which is called as the single phase induction motor and the split phase motor and also the two phase induction motor and the three phase induction motor I have already told you. So this is the graph that you always have to remember. I have already told this is for the three phase induction motor, this is for two phase induction motor, and this is for the single phase induction motor. I have already told these three different graphs. But now what I am going to do basically here is, now I am going to draw the extra graph which is called as a split phase motor. Split phase motor, now you can see it is not it is a self-starting motor, because even when the rotor speed is equal to 0 means we can say standstill condition, or we can say it is also called as the starting condition. Even though the rotor speed is equal to 0, we are going to get a non-zero torque. So we can say it is a self-starting. So this split phase or resistance split phase is basically a self-starting machine. So we can say it can self-start. So it is going to start like this after reaching certain speed. So after reaching certain speed, so therefore we are going to open the switch. So up to this time switch is closed. So therefore we are going to get, see, it is acting like a self-starting, and then this is the torque characteristics that we are going to get. After reaching certain speed, we are going to open the switch. Whenever the switch is open, so it is going to act like a single phase induction motor, because only one winding is there. So therefore we are going to get like this. So up to 0 to this certain speed. So before you close the switch, it is acting like a two phase induction motor. But after opening the switch, it is acting like a single phase induction motor because there is only one winding. So this is the important thing that you always have to remember. So we can say that this is the actual two-phase induction motor and this is a three-phase induction motor and this is a single phase induction motor. But before opening the switch, so for this period switch is closed, it is acting like a two-phase induction motor. But after that, it is purely a single phase induction motor. So the characteristics are going to get dropped and it is going to follow exactly like a single phase induction motor. So this is the beautiness of this one. So by adding this extra auxiliary winding, now you don't have to rotate it manually, you don't have to rotate it because it's a self-starting machine. So therefore we can say this is a very important point that you always have to remember. So before you open the switch, so whenever the switch is closed, it is going to act like a two-phase induction motor, but not exactly. But the characteristics is somewhat lesser speed when compared to exact two-phase induction motor. But whenever the switch is open, it is going to act like exactly single-phase induction motor. So its characteristics have become the exactly like a single-phase induction motor. So this is the beautiness of this circuit diagram, or you can say by this graph you can observe these many important things. So these split phase induction motor characteristics are going to lie exactly between the single phase induction motor and the two phase induction motor. I have already told you this split phase motor, induction type motor, two phase induction motor and the three phase induction motor are self-starting, whereas the single phase induction motor is not a self-starting because even the at starting condition or the standstill condition, the rotor speed is equal to 0, the torque is also 0. So we can say it is said to be not a self-starting machine. So these are the points that you always have to remember for your lifetime whenever you are present in this electrical engineering. So this is for the three-phase induction motor, two-phase induction motor, split-phase induction motor, and this is the single-phase induction motor. So now we are going to study about the capacitor start induction motor, capacitor start single-phase induction motor. So same thing, single-phase AC supply we are going to give. Here for this auxiliary winding, we are going to keep an extra capacitor. So extra capacitor we are going to keep here. It is called as a capacitor start. Means we are using this capacitor only for the starting purpose. So that is the reason it is called as a capacitor start induction motor, single phase induction motor. So this is the centrifugal switch. So this is the switching current. This is the current in this is called as a starting current, or we can say auxiliary current. And this is the main winding current, or we can say running current. And this is the main winding or running winding. So I already told you this is the squirrel cage induction rotor. So now I already told you this auxiliary winding is used only for starting purpose. So for production of the self-starting. So therefore you don't need to manually operate it. It's a self-starting machine. So therefore these two fluxes are going to get interact and we are going to get a rotating magnetic field. So it is going to rotate without any manual operation. It can rotate by itself starting. So therefore now if I want to draw the phasor diagram of this circuit, this is the supply voltage V. And you can say clearly IM is the main winding, is also called running winding. It has huge amount of reactance and less amount of resistance. So it is highly magnetizing. So current is going to lag very high. This is the IM. And now the current IS. So current is a capacitive circuit, is a inductor and capacitor, means overall it is going to act like a capacitive circuit. So therefore we can say because it's a highly resistive and the inductor is very less. So therefore capacitor is going to get dominate. So circuit is going to behave totally. This winding is going to behave purely like a more capacitor because resistance is very higher, inductor is very lesser, but capacitor is very higher. So it is going to behave like a capacitor circuit. So current is going to lead the supply voltage by certain angle. So now alpha is the angle between these two currents because IN is going to produce some flux, IM is also going to produce some flux. So the angle between these two fluxes is called as the alpha, or we can say torque angle or node angle. You can call any of this one. So starting torque is directly proportional to IM into IS into sine alpha. So now you can see clearly alpha is increased now. So when compared to previous case, in the previous case alpha is very less, but now alpha is increased. The previous case alpha is very less, but now alpha is increased. As alpha increases, sine alpha increases, so starting torque is further increased. So with the help of capacitor start motor, the starting torque is further increased. That is the beautiness of this concept. So therefore, whenever a switch is closed, this is a phasor diagram we are going to get. In the split phase or resistance split phase, the alpha is very less, but now the alpha is increased to a very high value. As alpha increases, sin alpha increases, so starting torque is also increases to a huge value. So whenever the alpha is equal to 90, we are going to get the maximum torque or maximum starting torque. So maximum starting torque whenever the alpha is equal to 90 degree, you can see clearly from this expression. So whenever the alpha is equal to 90 degree, then we can say starting torque was very higher. So now I am going to compare the two things, which is called as a split phase or resistance split phase and a capacitor start motor. So you can see clearly, which is the figure, you can see clearly this is for the capacitor start and this is for the resistance start, or you can say split phase. This is the previous one and this is the new one. So now if you see clearly, one important point I have already told you here, alpha of this capacitor start is very higher than the resistance. So its starting torque is very higher when compared to this one. So it is moving upward, and here the graph is shifting upward. The overall graph is going to get shift upward. So like this we are going to get. So like this we are going to get. So this is the diagram we are going to get. So this is the diagram we are going to get whenever the switch is closed. But whenever the switch is open, it is going to act like a purely single phase induction motor. So the characteristics are going to become a little bit downer. So therefore, otherwise, whenever the switch is closed, it is behave like a two-phase winding, so two-phase induction motor. So therefore, we can say this graph is going to lie between the exactly single phase and between the exactly two phase. So you are going to get graph like this. But whenever the switch is open, it is going to exactly behave like a single phase induction motor. So the characteristics are going to come a little bit downer. So this is the point that you always have to remember. Whenever the switch is closed, it is going to act like a two-phase induction motor. So these characteristics are going to lie between the single phase and the two phase. So the characteristics are a little bit higher. Whenever the switch is open, it is exactly behave like a single phase induction motor. So the characteristics are going to come a little bit downer. So this is the thing that you always have to remember. In a capacitor start, the starting torque is very higher because alpha is very higher. So the starting torque is very higher. So that is the reason this graph is shifted upward when compared to previous one. So now after reaching certain speed, the centrifugal switch is going to open automatically. Automatically it is going to get open. So now we can say whenever the switch is closed, it is going to follow the three-phase induction motor characteristics, and whenever the switch is open, it is going to follow like single-phase induction motor characteristics. So we can say clearly, whenever the switch is closed, it is going to follow exactly like a two-phase or three-phase induction motor characteristics, whereas whenever the switch is open, it is going to follow exactly like a single-phase induction motor characteristics. So these are the points that you always have to remember. So starting torque TS1 is always greater than the starting torque TS2. So we can say these two motors are said to be self-starting because even the rotor speed is equal to 0, at standstill or starting condition, the torque is not at all equal to 0. So we can say this is said to be a self-starting machine. So whenever the switch is closed, it is behave like a two-phase or three-phase induction motor, whereas the switch is open, it is going to follow exactly like a single-phase induction motor characteristics. So this graph looks somewhat similar to two-phase and also between the three-phase also. So we can write go for two-phase or three-phase, anyhow it is same. So now we will go for the other case, which is called as the capacitor start and capacitor run. So here capacitor start and capacitor run. So basically it means that we are using the capacitor for both starting condition and also for the running condition. Then we will see what is going to actually happens, and then we will see what is going to happen. So therefore, if the capacitor is used for starting purpose and also for running purpose, then we will see what is exactly is going to happen. So now this is the single phase AC supply, this is the auxiliary winding, and this is the main winding. So this capacitor is used for both starting purpose and also for running purpose, and the current in this auxiliary winding is IS and the current in the main winding is IM. I have already told auxiliary winding is also called the starting winding. So we can write IS current, and the current in the main winding is called as IM. Main winding is also called as the running winding. Starting winding has huge amount of resistance and less amount of reactance, electric reactance. Whereas the main winding has less amount of resistance but huge amount of magnetizing reactance. And I is the overall supply current. So now there is no centrifugal switch. So now we are going to draw the phasor diagram of these currents and voltages. So this is the supply voltage V. As I have already told you, main winding is hugely inductive reactance. So current is going to get lag. IM is going to lag the supply voltage. Whereas this auxiliary winding, I have already told it's a more capacitive in nature because the auxiliary winding has huge amount of resistive but less amount of magnetizing reactance. But here it is going to have more capacitive, so IS is going to lead the supply voltage. So if you see clearly alpha, see alpha is the angle between the IS and IM, because IS is producing some flux, IM is producing some flux. So the angle between these two fluxes is called as the alpha. But now alpha is further increased when compared to previous case. So if you use the capacitor for starting purpose and running purpose, alpha is nearly equal to 90 degree. In the first case alpha was very less, in the second case alpha was further increased, and now the alpha was more further increased to its maximum value. So whenever the alpha is equal to 90, I have already told you the starting torque will be maximum, because starting torque is directly proportional to Im into Is into sin alpha. So your alpha is very higher, so therefore the starting torque will be further and further and further more higher. So the characteristics are going to shift more upper direction. So now we will analyze whatever the three things that we have learned. So all the three graphs we are going to draw consecutively and see what is going to actually happens. So now we can see clearly, as I have already told you, this is the graph for a split phase motor or resistance start motor, and this is the graph for a capacitor start and capacitor run motor, and this is for the capacitor start motor. So you can see clearly this capacitor start and capacitor run motor characteristics are going to lie in between these two things. Even though alpha is nearly equal to 90, but still its characteristics are going to lie in between the first and the second. So this third characteristics are going to lie between the first and the second. So therefore this is called as the split phase motor or resistance start motor, and this is called as the capacitor start motor, and this is called as the capacitor start and capacitor run motor. So therefore we can say here the rotor speed is equal to 0 and the rotor speed is equal to synchronous speed. So whenever the rotor speed is equal to synchronous speed, slip is equal to 0. Whenever the slip is equal to 0, the torque is nothing but 0. So therefore these characteristics are called as the capacitor start and capacitor run motor. Its characteristics are similar to a three-phase induction motor characteristics. So you can see clearly its characteristics is similar to that of a capacitor, or you can say three-phase induction motor, because here switch is not at all present. So here switch is not at all present. Always capacitor is going to present. So its characteristics is similar to that of a three-phase induction motor characteristics. So as the switch is not there, so we can say that simply means the switch is not at all there. So therefore we can say that its characteristics similar to that of a three-phase induction motor characteristics. So you can say clearly it is similar to a three-phase induction motor characteristics. Whereas the split phase motor or resistance start motor and the capacitor start motor, here up to certain speed they are going to act like a two-phase induction motor, but after that they are going to act like a single-phase induction motor characteristics. So that there will be dip in the characteristics. Here also there will be certain amount of dip in the characteristics. So whenever the switch is closed, they are going to act like a two-phase induction motor, but after that they are going to act like a single-phase induction motor. For the split phase motor or resistance start motor and also the capacitor start motor. Whereas this one, capacitor start and capacitor run motor, there is no switch, so definitely it is going to, these characteristics look similar to that of a three-phase induction motor characteristics. But its starting torque is less, it is going to lie between these two. So the starting torque is going to lie between these two. So now we are going to discuss about the shaded pole induction motor. Shaded pole induction motor means, you can see clearly here there are two poles in this manner. So we are going to split this pole into, one is bigger size and the other is the smaller size. So this is also, the pole is going to, we are going to cut into two types of poles. One is smaller pole and the other is the larger pole. And here we are going to keep a field winding. So here we are going to keep a field winding, and then that winding we are going to take here, again we are going to wind it here, and then we are going to take it outside. So this is called as a single phase AC supply. But here on the smaller poles, we are going to use some copper coils, and we can say these are called as the shading coils, or simply we can call it as some copper bands, or we can say conductor bands, like a closed conductor band. So we are going to keep it here and also here. So this is called as it is made by copper, or we can say it can also be made by aluminium. Copper or aluminium, you can use anyone. So always there is a rotation from always non-shaded to shaded coils. So from non-shading to shaded coils, you can see clearly like this it is going to get rotated. So from non-shading part to shading part, there is a rotation of the RMF, or we can say the flux produced by the single phase winding and the flux produced due to these copper windings because of uneven flux. So because of uneven flux between these poles and this pole, between the big pole and the small pole, between this big size pole and the small size pole, the uneven flux is going to get produced. So because of that, there is a rotation of this rotor. So because of this, we can say that there is a rotation in the rotor which is present in the between them. So we can say that by using these copper sheeting coils, we are going to make the uneven distribution of flux between this bigger size and the smaller size. So because of that, there is a rotation of the rotor we are going to get. This is called as a shaded pole induction motor, because we are going to shade one of the pole with the help of copper bands or aluminum bands. So because of that, there is an uneven distribution of flux between these two poles. So because of that, this is going to rotate in this way. So now we will analyze the different types of torque diagrams of each and every thing. So always from non-shading part to shading part, it is going to rotate. So from non-shading part to shading part, it is always going to rotate. So this is the thing that you always have to remember. This rotor is always going to rotate from non-shading part to shading part, non-shading part to shading part. See, once the shaded pole is fixed, once the design is fixed, always the rotation is always in a one direction. You cannot change the direction. This is the point that you always have to remember. Once the motor is fixed, once you fix each and everything, then the rotation is always in one direction from non-shading part to shading part. You cannot change the direction of the rotation in a shaded pole induction motor. So always the direction of rotation is from non-shading part to shading part. So that is always the direction. You cannot get the reverse direction. In a shaded pole motor, you cannot get the reverse direction. Only it is a unidirectional motor, only from non-shading part to shading part. You will never get the from shading to unshading. You will never get like that. Always from non-shading to shading part. This is the point that you always have to remember. So now I am going to compare each and everything, torque speed characteristics of different motors. See now here, this is called as a shaded pole motor. This is called as the shaded pole motor. So this is the shaded pole induction motor, and this is called as the basically resistance split phase motor. I already told this one, and this one was called as the capacitor start and capacitor run. So this is called as the capacitor start and capacitor run, and here this one is called as the capacitor start. So you can see clearly. This is called as the shaded pole. This is resistance split phase, and this is called the capacitor start, and this is the capacitor start and capacitor run. So these are the torque speed characteristics. So you can see clearly, whenever the rotor speed is equal to 0, each are having a non-zero torque. So we can say all these are self-starting motors. All these are self-starting induction motors. So this is the point that you always have to remember. These characteristics are going to lie exactly between the, see, this here we are going to get single phase, and here we are going to get two phase, and here we are going to get three phase. The remaining things are always going to lie between the single phase and the two phase. All these graphs are going to lie in between the single phase, exactly single phase and two phase. So this is exactly this is the single. So if you draw a line in this format, so I have drawn each and every characteristics. So you can see clearly this first one is called as the single phase induction motor. It is not a self-starting, because when all the rotor speed is equal to 0, its torque is also 0. So it is not a self-starting. And this is called as the shaded pole induction motor. And this is called as the resistance split phase induction motor. And this is called as the capacitor start induction motor. And this is the capacitor start and capacitor run induction motor. Here basically in this diagram we are going to use two types of capacitors. One is for starting purpose and the other is for the running purpose. I have drawn this, I have not drawn this graph in this actual one, but you can see in my other classes where you can see that one. So therefore, you can, if you see my ISRO question paper, you can see the exact diagram of a capacitor start and capacitor run induction motor type. So here this is called the capacitor start, and this is two-phase induction motor, and this is the three-phase induction motor. So we can say clearly all these characteristics are going to lie between the single phase and the two phase. So this spike is nothing but before see, the spikes are indicates that this period is for before the closing. See, this is the closing of switch and this is the opening of the switch. Whenever the switch is open, this is going to act like a pure single phase induction motor. So the characteristics are going to get some little bit deeper. They are going to come downer. That is the thing that you always have to remember. So this is the single phase induction motor, shaded pole induction motor, split phase induction motor, the resistance split phase induction motor, and this is the capacitor start induction motor, This is a capacitor start and capacitor run induction motor. This is a two-phase induction motor and this is the three-phase induction motor. So this shaded pole induction motors, resistance split phase induction motor, capacitor start and capacitor run and the capacitor start, all these are self-starting induction motors. Some important points for the split phase induction motor. So split phase induction motor is also called as a resistance split phase. So now we will discuss some important points regarding this one. You have to always remember these things. So for reverse rotation, do these following things. So if you want the reverse rotation, do these following things. Reverse the main field winding terminals only. So just reverse the main field winding terminals only, because if you reverse the main field terminals, the flux of this is going to get changed. So whenever the fluxes of this is going to change, I have already told you, torque is directly proportional to Im into Is into cos of alpha. As Im changes, the overall torque is also going to get changes. Whereas reverse the auxiliary field winding terminals only. So just if you do the reverse of auxiliary field winding terminals only, so you have to change any one of them, but not both of them. If you change both of them, negative to negative is again positive. So that is the reason you have to change only one, not both. So therefore, reverse the main field winding terminals only, or reverse the auxiliary field winding terminals only, but not both. Interchange the capacitor from auxiliary winding to main winding. You can change that. You can interchange the capacitor from auxiliary to main winding also. Then also this is going to get possible. So interchange the capacitor from auxiliary winding to main winding also. You can do like that. You can get the reverse rotation. And the reverse rotation won't possible if you do these things. So these are the things that you can do in order to change the direction of rotation of the rotor. Just you interchange the main field winding terminals, or just interchange the auxiliary field winding terminals, or interchange the capacitor from auxiliary winding to main winding. You can do any of these three. Only one you have to do out of these three. So therefore you are going to get. You don't have to do two things. So you don't have to interchange two things to get this one. So reverse rotation won't possible if you do these below things, which are reverse rotation won't possible if you do these things. Reverse rotation both main winding and auxiliary winding. So if you interchange, or you can say if you change terminals of the main winding and auxiliary winding at the same time, you are going to get negative and negative is positive. So it will never get reverse rotation. Reversing the capacitor terminals. So just by reversing the capacitor terminals, you will never get the change in the rotation. And reversing the supply terminals. If you reverse the supply terminals, Im is reversed, Is is reversed. Again we are going to get negative to negative is positive. So therefore, you are not going to get the reverse rotation. So therefore, this reverse rotation is possible only when if you interchange the main field winding terminals alone, or auxiliary field winding terminals alone, or interchange the capacitor from auxiliary to main winding. But the reverse rotation won't possible if you do the reverse rotation of both the main winding and auxiliary winding, or reversing the capacitor terminals, or reversing the supply terminals, because torque is directly proportional to Im into Is into sin alpha. So Im into Is into sin alpha. This is the point that you always have to remember. So if Im is reversed, then torque is reversed. If Is is reversed, torque is reversed. If both are reversed, torque will never reverse. So this is the point that you always have to remember. If you reverse the supply terminals, Im is reversed, Is is reversed. So negative to negative is again positive. So it will never change the rotation. Just by reversing the capacitor, just by reversing the capacitor terminals, nothing will happen, because Is remains the same direction. So therefore, by reversing the both the main and winding, Is is reversed, Im is also reversed. So therefore, simply we can say that again we are going to get the same torque. So therefore, there will be no changing of rotation. So now we are going to study about the stepper motors. So stepper motors is called as this is the diagram of a stepper motors, means the rotation is in terms of the steps. That is why it is called as a stepper motor. So this is the stepper motor. So you can see this is the stator. So this is the three windings we are going to use. So listen carefully. These are the three windings that we are going to choose here. So this is the winding like this we are going to wound, and then we are going to take it from here and we have to take it to the terminal A. Similarly, this is the another winding. So this is the another winding we are going to wound it like this. Again we have to wound it like this, and we have to keep it to the terminal B. Again we are going to take the another winding. Again we have to wound it like this. Again the coil we have to take it here. Again we have to keep it to here C. So we can say these three terminals are connected to a common point, and these three terminals we can connect to any other point based on the configuration. So therefore, this is the switches here. So then we are going to give DC supply. So here we are going to give variable DC supply. So it is a microcontroller drive circuit or switching circuit. So it is basically a microcontroller drive circuit or switching circuit. Input is a DC supply, but we are going to get this rotor is in terms of this format, like steps we are going to get. The rotation is in terms of the steps. So this is a microcontroller drive circuit or a switching circuit. We can control the amount of switching here. So we can control. So this is the phase A winding, this is a phase B winding, and this is the phase C winding. So you can see the phase angle between the windings is 120 degree. So this is the phase 1, phase B, and phase C. You can see the angle between them is 120 degree. So therefore now you can go for switching of any of these A, B, or C based on the things that you really want here. So therefore, if you keep the switch A, phase A winding is, you can say, triggered. If you close the switch B, phase B winding is triggered. If you switch on the switch C, the phase C is triggered. So it is going to rotate based on the excitation you are going to give. It is going to align itself based on the excitation that you are going to give. If you give the phase, if you close the switch A, it is going to be in this direction. If you close the switch B, this is exciting, so it is going to turn and it is going to be in the direction of this one. And if you switch on the switch C, this winding is going to get excite, so it is going to turn itself and move in this direction. So we can say it is in terms of a steps. So therefore, this is called as a switching circuit or microcontroller or driving circuit or switching circuit. It is also called as a microcontroller or driving circuit or switching circuit. It is going to align itself in the direction of the magnetic field. So let me draw another diagram here. So this is the DC supply. Here we are taking like this. Again we have take it like this, and we have to connect to here. Again we have take another point. Again you have to move here. Again you have to move here. Again you have to connect to here. Let me assume this is switch A and this is switch B. Here we are going to use a circular rotor. Suppose if this winding is excited, if I close the switch, this winding is excited, so therefore it is going to align in this direction. Suppose if I close the switch, this winding is excited, so therefore it is going to align in the direction of this one. So we can say that this is going to rotate as the field is present. So in whichever the resultant field direction is present, it is going to align itself in that direction. So that is the meaning of this one. So therefore, but if you see clearly, this microcontroller is in the circular fashion. This rotor is in the circular fashion, whereas in the previous one it is in the format of a step fashion. So this is the microcontroller driving circuit or switching circuit. Alpha is called as the ns minus nr by ns into nr into 360 degree. So this is the important formula that you always have to remember. Alpha is called as the step angle or step size. How much amount of angle that rotor is going to move. So how much amount of mechanical angle that it is going to rotate. So how much amount of mechanical angle that rotor is going to move. Alpha is equal to ns minus nr by ns into nr here into 360. Or simply we can use another formula, 360 degree by m into nr. We can use any of this formula. So alpha is equal to ns minus nr by ns into nr into 360 or 360 degree by m into nr. So alpha is equal to ns minus nr by ns into nr into 360 degree or 360 degree by m into nr. You can use any of this formula. Or alpha is called as the step angle or step size. So alpha is equal to ns minus nr by ns into nr into 360 degree or 360 degree by m into nr, where alpha is called as the step angle or step size. So ns is called as the number of stator poles, or we can say number of phases on stator. So ns is called as the number of stator poles or number of phases on stator. nr is called as the number of rotor poles or number of rotor teeth. And m is called as the number of phases in stator, or we can say number of sets of windings on stator. See, this is the very important formulas that you always have to remember. Alpha is equal to ns minus nr by ns into nr into 360 degree or alpha is equal to 360 degree by m into nr, where alpha is called as the step angle or the step size, and ns is called as the number of stator poles. Ns is called as the number of stator poles, or we can say number of phases on stator. Ns is called as the number of stator poles or number of phases on stator, and nr is called as the number of rotor poles or number of rotor teeth. M is called as the number of phases in stator or number of sets of winding on stator. So alpha is called as the step angle or step size, and ns is called as the number of stator poles or number of phases on stator, and nr is called as the number of rotor poles or number of rotor teeth, and m is called as the number of phases in stator or number of sets of windings on stator. So these are the formulas that you always have to remember. Alpha is equal to ns minus nr by ns into nr into 360 degree. is equal to 360 degree by m into nr. Always called the step size or step angle. Ns is number of stator poles. Ns is called as the number of stator poles. Number of stator poles means number of poles which are present on the stator, or number of phases on stator means how many number of phases are going to present on the stator, or we can say number of poles on stator or number of phases which are present on the stator. Ns is called as the number of stator poles or number of phases on the stator. Nr is called as the number of rotor poles or number of rotor teeth. Number of rotor poles or number of rotor teeth. And m is called as the number of phases in stator. M is called as the number of phases in stator, or we can say number of sets of windings on stator. So like this you can use here. Ns is called as the number of stator poles. Nr is called the number of rotor poles, and m is called as the number of phases in stator. Ns is called the number of stator poles. Nr is called the number of rotor poles, and m is called the number of phases in stator. So like this you have to always remember. So suppose for 4 steps means alpha is equal to 360 by 4, it is nothing but 90 degree. So each step has an angle of 90 degree. So for 4 steps means how much is the alpha is nothing but 360 by 4 is equal to 90 degree. So for one step we are going to have 90 degree. Suppose for 12 steps alpha is equal to 360 by 12, which is 30 degree. So each step has a angle of 30 degree. So this is the easy way. So therefore for 4 steps means alpha is equal to 360 by 4, which is equal to 90 degree. So each one is going to have 90 degree. So for 12 steps, so each one is having a alpha is equal to 360 by 12, which is called as the 30. So types of stepper motors are variable reluctance stepper motor, permanent magnet stepper motor, and hybrid magnet stepper motor. So these are the different types of stepper motors which are available. The types of stepper motors are the variable reluctance stepper motor, permanent magnet stepper motor, and the hybrid magnet stepper motor. So types of stepper motors are variable reluctance stepper motor, permanent magnet stepper motor, and the hybrid magnet stepper motor. So these are the different types of stepper motors that we are going to see in the market. So this formula is very important. Let me repeat this one. Alpha is equal to ns minus nr by ns into nr into 360, or 360 degree by m into nr. So therefore alpha is called as a step angle of the step size, and ns is called as the number of stator poles, nr is called as the number of rotor poles, and m is called as the number of phases in the stator. Ns is also called as the number of phases of stator, nr is called as the number of rotor teeth, or m is called as the number of sets of windings on the stator. So like this you have to always remember. Ns is called the number of stator poles, nr is called the number of rotor poles, and m is called the number of phases on stator. Or ns is also called as number of phases on stator, and nr is also called as the number of rotor teeth, and m is also called as the number of sets of winding on stator. So these are the different things that you always have to remember to solve the questions based on this concept. So these are the very important formulas of the and the concepts revision in a very detailed manner of induction machines in a very detailed manner. So if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button, so whenever we upload a new video, the direct notification comes on mobile. If any improvements needed in our video lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smile and take care, and bye bye.